Hi everyone and welcome back to NTE. In today's video what we're going to do is we're going to be looking at the May-June past paper, right, and this is Mathematics paper 1, right. What I'm planning to do is to just run through the entire paper from start to finish without any stop, right. Now, before we begin, just a few things to note, right? If you go to the comment section and also in the description box, you'll find timestamps, right, which will help you to navigate through the video a little bit quicker, right? Basically, you just click on the time and the video will automatically skip to that specific question, right? If there's a specific question that you're interested in the solution of, right? Secondly, if you want to benefit the most out of this video, one thing that you can do is to actually dedicate a day for yourself where you sit down with the question paper and do it yourself before you use this audio memo to check your solutions, right? A second option is to pause the video right before I'm about to go through the solution and actually try the question yourself, then press play and check yourself. Okay. And so with that said, let's jump right into it. Okay, so question number 1, right, 1.1, we're asked to solve for x. Okay, question 1.1.1, right, is quite an easy one, an easy introduction to this paper, right. So we see over here that we have two, right, brackets, okay. These are called factors, right, and we have this equal to 0, right? So we know that the step that came before this is that we had some sort of a quadratic. They've now factorized it for us, right? And since this is equals to 0, we can now go straight into the next step, right? Because we know that if we have two factors, right, being multiplied with each other equal to 0, that means that it's either this first factor, right, 3x minus 1, either this one is equals to 0 or the second one is equals to 0, right? Either of them being equal to 0 will result in this overall output of 0, right? So then therefore we can now solve for x from here. Okay, we're going to have two different solutions. The first one is going to be when x is equals to 1 over 3. And the other one is going to be when x is equals to negative 4. Okay. All right. Next question. Right. 1.1.2. Right. Again, we're asked to solve for x, but this time we are given a quadratic. Right. Again, we see that it's equals to 0. Okay. So which means that there is no rearranging that we have to do. Okay. We purely just need to go into the step of factorizing this quadratic. But hold on. We're given a little tip over here, right, that we need to write our solutions for x correct to 2 decimal places, right, which means that this specific quadratic that has been given to us doesn't have rational number solutions, so which means we can't put it into two brackets like we had in the previous example. Okay, so we're going to have to use a different method, right, to solve for x in this case. And one of the easiest methods that we use, right, is that wherever we have such a trinomial, we solve for x by applying the quadratic formula. Okay. Okay, so if we just remind ourselves very quickly what the quadratic formula says, right, we know that x is going to be given by the solutions minus b plus or minus the square root of b squared minus 4 times a times c, all of this divided by 2 times a. Okay, so from our given equation, right, we just need to identify, okay, we'll just rewrite it, 2x squared plus 9x minus 14. This is equals to 0. Okay. Our task is just simply to identify our a, b, and c value. Okay. And a is always the coefficient of x squared, right? B is going to be the coefficient of x. There it is. And lastly, c is our constant term. There it is. Okay. Right, so be careful with negatives, right? Some people will take C as just 14, right? If you have a minus sign there, it is that negative is part of C. Okay, we can rewrite it if you want to, right? So remember that all of these values come from just thinking of the standard form ax squared plus bx plus c, right? So this is the standard form. Notice that everywhere here you have plus signs right in between your terms, okay? So what they do is sometimes you will have negatives right in between your terms. So if you want to rewrite that in order for you to see clearly what's happening, if you want to make it exactly like this, right, then you would rewrite it as 2x squared, right, plus 9x plus a negative 14. Okay, now you can see that you have this in exactly standard form, right, where you have plus signs in between all of your terms. Okay, so then yet again we can now quickly identify that this will be A, okay, this will be B, and this will be C. Okay, so once you work with these equations quite a lot, you're able to do that identification quite quickly. Okay. So then from there, right, let's just write over here, A, B, and C. Okay, so from there you just write down your quadratic formula. Okay, you say x is going to be equals to minus b plus or minus the square root of b squared minus 4 times a times c, all of this divided by 2 times a. Okay, now you just substitute in all these identified values. So you have minus, b in this case is just a positive 9. You're going to have plus or minus the square root of 9 squared, okay, minus 4 times your a value is 2 times your c value of negative 14. And all of this will be divided by 2 times 2. Okay, now it's up to the calculator to evaluate this. Okay, so we know we're going to have two solutions. Okay. Okay, so when you work that out in your calculator, you'll get that your first solution is x is equals to 1.22, right? Sticking to this instruction of correcting 2 decimal places. And you also get that x is equals to minus 5.72. Okay. Another thing you can do just to check yourself really quickly before you move on, just to make sure you didn't do any calculator errors, is to take these two numbers, plug them back into this original right equation given to you over here, and make sure that you get an output of 0 or approximately 0 because you've rounded off over here. Okay, right. Before we leave this question, right, another method that you can use is to solve this by completing the square, right? And remember that if you decide to take the method of completing the square, be very careful about the coefficient on your x squared term, right? You can see that it's currently 2. You would first have to pull out that coefficient of negative 2 and make that coefficient of x squared to equal 1 before you begin the process of completing the square. But I'll leave that method up to you, right, to try if you want to. Okay. Question 1.1.3, right. We are now given a radical equation, right, and when I say radical equation, I'm talking about this sign over here, okay, this square root sign over here makes this something called a radical equation. Okay. So we are still going to be solving this using the methods that we know, right? So basically application of inverse operations, but there is one extra step that these type of equations put in or need, right? And that is the fact that you need to remember that whenever you're dealing with a radical equation, you have to test, right, your values, okay, and make sure that you don't end up, okay, with a negative under the square root. Okay, so that's one thing that's very important. Okay, here, right? We don't want this. Okay, this is something that we don't want. Right. So let's go about solving this. Okay, I'm going to rewrite it first. Okay, so we had the square root of 3 minus 26x, right, and this was equals to 3x. Okay, so what's going to be our first step over here? Well, our first step is going to apply an inverse operation, right? And the inverse of square rooting is to square both sides. Okay, there we go. Right, now once we've done that, okay, because these two are inverse operations, they cancel each other out. Okay, the square root and the square cancels each other out, leaving you with what's inside of the radical, 3 minus 26x. And that's going to be equals to, well, over here now what we're doing is we are applying exponential laws. Right, we have this exponent of 2. We're going to have to distribute it to the 3, right, so the base 3, and distribute it to the base x. Okay, 9, right, x squared. Okay, so now notice that you now have the 3 elements of the quadratic, right? You have an x squared term, you have an x term, and you have a constant term. So what you're going to do to solve this is to move all of these variables, right, all of these ones, move them to the other side so that you can set this equals to 0 and just solve it like a quadratic that we are used to. Okay, like the previous two questions basically. Okay, so we're going to have 0 on this side, and this is going to be equals to 9x squared. Okay, then you're going to have plus 26x, and then you're going to have minus 3. Right. Right, so now we have ourselves a quadratic here on the right hand side that we can solve for. Okay. Unfortunately, 26 is not a multiple of 3, so we couldn't divide through by 3 to just flatten this quadratic out or to simplify it further. Okay. And you might be able to factorize it. Let's just see. Right, so if we think of the number 3, right, this number 3 is actually a prime number, right? So, which means that it only has the factors 1 and 3. Okay, so if we think of this, we try and put this into 2 brackets. We can only have the factors 1 and 3, okay, that can multiply to give you 3, right? Now, if we put 9x over here, okay, and we multiply 9 by 3, we know that we'll get 27. Okay, so which means that what we have now in our hands is a 27x. Okay, we want to get 26x as a middle term, so it will be a good idea to have a positive 27x, right? And then after that, subtract, right, working backwards, just one of those x's. Okay, so if we have 27x minus an x, that will give us this middle term of 26x. Okay, so those are now the two factors of this previous quadratic, right? This now takes us back to the same setup that we had in question 1.1.1, right? 2 brackets equals to 0, giving us 9x minus 1 is equal to 0, or x plus 3 is equal to 0. Okay, so then therefore x is going to have to be equals to, from this first side we have 1 over 9, and the other side we have x is equals to minus 3. Okay, now remember that we said in the beginning that we need to check that neither of these solutions, right, we need to check basically if any of these solutions give us a negative underneath the square root. Okay, let's check 1 over 9 in our calculator. Right, so you're going to put into your calculator the square root of 3 minus 26 times 1 over 9. Okay, and you get 1/3 as your answer. Okay, so that's fine. On the other side, we have 3 times 1/9. Okay, which also gives us 1/3. Right. So this first solution is fine because it doesn't give us a negative underneath the square root, and also the right hand side is equal to the left hand side. Let's check the second one. Right, so on your calculator, square root of 3 minus 26 times -3. Okay, that gives you a value of 9. Okay, that's fine. What about the other side? 3 times -3. Okay, that gives you a value of -9. Okay, so this one, we're going to have to reject this. Okay, so we're going to write here not applicable, right? And the reason for this is because, right, since the left hand side is not equal to the right hand side. Okay, and you would have seen that for the left hand side you get a value of 9, right, and the right hand side you get a value of -9, right. These two things are not equals to each other, so this solution over here does not satisfy the original equation, right, this one that we were given. Okay, this original equation. Okay, next question, right, question 1.1.4. Okay, again we're solving for x, but now we need to notice that we are no longer in equations, right, we are now in the realm of inequalities. Okay, all right, so what do we have going on over here? We have these two factors, right, x minus 1 and x minus 4. Okay, we want to know when is this greater than x plus 11. Okay, so whether we like it or not, we have to distribute these two brackets out, right, because we need to combine this, okay, with the common factor of x and sort of not common factor but like term of x and this like term of 11. Okay, and we'll then have this being greater than 0, right? So then we're just going to be evaluating that resultant quadratic. Okay, we want to know when is that resultant quadratic going to be positive. Okay, so let's do that quickly. So if I just rewrite our question, okay, we have x minus 1 times x minus 4 greater than x plus 11. Okay, so if we distribute this out, you get x squared, right? Minus 4x minus an x is minus 5x plus a 4, right? Greater than x plus 11, right? So similar to just rearranging equations, we're going to subtract x on both sides and subtract 11 from both sides, right, which will give us x squared, right. Then we now have minus 5x minus x is minus 6x. Okay, and then we have 4 minus 11, which is minus 7. And now this is now greater than 0. Okay, so this is what I was talking about. Right over here, we now have a resultant quadratic. Okay. Alright, so now we are now concerned about where is this quadratic, okay, positive. Okay, so we are now going to have to factorize this, okay, and what we're looking at here is 7. 7 is also a prime number. That's very nice because then we're dealing with the factors 1 and 7. Okay, so we have x and x, right? We have 1 over there, we have 7 over there. Okay, that's greater than 0, right? We want a middle term of -6, so which means that we're going to need -7 plus 1, right, to give us a middle term of -6. Okay, now the options that you have, right, to carry on from here is two different options. Let's just write them down. Okay, so option 1 is to use a number line. Okay, and option 2, okay, is to use a sketch. Okay, so in between these two steps, just make a space over here. Right, what we actually had to do is to evaluate our critical numbers. Okay, so we're going to say over here, right, for critical values, okay, we're going to have x plus 1 equal to 0 or x minus 7 equal to 0. Okay, giving us a critical value at negative 1, right, and another critical value at 7, right. So on option number 1, what you would have is your number line, right, containing these two critical values, negative 1 over there and 7 over here, right. If you were using option 2, then these critical values, right, so these ones, okay, these are actually the x-intercepts, right, of your sketch, right, your parabola basically. Okay, so if you were using option number 2, you would draw yourself a nice little Cartesian plane. Okay, and you would obviously still put these critical numbers in, so that's negative 1, 7 would be somewhere there, right, and then you would go back to this green box over here, because this is actually the quadratic that you're going to be sketching, right, and notice that you have a negative 7 as your y-intercept, right, so that's going to help you to draw an accurate sketch, right, of cutting in the negative y-axis, right, so you would go through here, would cut there, you would turn somewhere, and then come back through. Right, let's just try it again. Okay, so that is your sketch of this function here in the green box. Okay, alright, so on the number line, right, if you wanted to use the option of the number line, okay, then how we would go about from here, right, our next step would be to just pick test values, right, within each of these 3 regions. Okay, so something like, don't choose numbers too far away, make it easy for yourself, right, so something like -2. A 0 is always a nice number to pick in between the 2 values, and just something greater than 7, so like 9, right. And the method here is really to substitute these test values into the brackets, right, or the factors, sorry, x plus 1 and x minus 7, okay, and evaluate the signs, right, in each region. Okay, so let's go for that. If we substitute -2 into this first bracket, we'll have -2 plus 1, which is going to be a negative result. If we substitute -2 in there, you can see you're going to have a negative result as well. If you substitute 0 in there, you get a positive result. 0 in there gives you a negative result. 9 in this first bracket is a positive result. 9 in the second bracket is also a positive result. Okay, but now we also need to add an extra step of evaluating an overall sign. Okay, and that's because we have 2 factors, right? So we're going to do that by multiplying the signs in each region, okay, because our factors are being multiplied with each other. So we have negative times negative, right, giving us an overall sign over here of positive region. Positive times negative gives this as a negative region, right? Positive times positive gives this as a positive region. Okay. Right, so then from there, we are able to write down our answer, okay, and say, therefore, okay, so we're going to go back over here, right, and we see that we are looking for greater than 0, right, and simply strictly greater than 0, right, so we're looking for these positive regions, right, so we are going to be at our critical point, right, with an open circle, identifying our positive regions as this side and this side, okay, and because we're just looking at strictly greater than, we're not going to shade in these open circles. They're going to remain open because that indicates that these two critical values are not included in our solution. Okay, so then we just write down our answer, okay, and the way you write down your answer is up to you. Okay, you can use inequality, right, so you can write down your answer using inequality. Okay, and that's going to look like this, right? So you're basically just going to say x, right, simply just less than -1, or x greater than 7. Okay, so that's writing your answer using an inequality, right? If you wanted to, you could also give your answer in something called interval notation. Okay, so if you give your answer in interval notation, you're going to have x as an element, right, of negative infinity up to -1, open brackets as well, because it's not included, together with, right, from the solution of 7 up to positive infinity. Okay. So now you can see that if you use the sketch, right, you will still get to these same results, right, these same solution sets, right, because with the sketch, right, if you're looking for where this parabola, right, x squared minus 6x minus 7, let's just write that in. This parabola is described by x squared minus 6x minus 7, right. It's very important to know, okay, which one of these equations that you are dealing with, which one actually indicates this parabola, okay, just so that you don't make a mistake. Okay, so now if you are interested in where it's positive, right, so where it's greater than 0, you're looking for where the graph of the parabola, okay, is in the region above, okay, this line. We all know that this line, okay, the x-axis is also defined by the equation y is equals to y is equals to 0, okay. So if you are looking for greater than 0, you're looking for the region right above this line, okay, so which is going to be this region over here. Okay, so that's where your function is above, okay, the x-axis or the line y is equals to 0. So you can see that this is basically y, okay, this is basically the region y greater than 0, okay, and y in this case is this function x squared minus x minus 7, okay. So if you're looking at that region over there, then you are looking for these parts of the graph, right, so that part of the graph and that part of the graph. Okay, so because you are not interested in it intersecting the x-axis, then you have open circles here and here at the x-intercepts, and then you're looking for all of these solutions, right, to the left of -1 and to the right of 7, okay, which is the same thing as what we did in this step. Okay. Right, next question. Okay, so in question 1.2, right, we are asked to simplify fully this expression over here. Right, So we have the square root of 16 times x to the exponent of 7 minus the square root of 25 times x to the exponent of 7, all divided by the square root of x. Okay. Now, with this, right, this is basically just grade 11 work. Okay, and really what they want you to see over here is that you're able to apply the rules of surds and also your exponential laws as well. Okay, so let's jot down the exponential laws and the rules of surds that you're going to use, okay, in order to solve this question. Okay, so these are the two, right, surd or exponential laws that we're going to need, okay, in order to simplify this question over here, right. The first one is the one that talks about the distribution, right, of a surd over multiplication. Okay, so if you have two factors underneath, right, we'll just keep it simple and talk about the square root, right. But this also applies if this was a cube root, okay. If you have the square root of two factors right underneath there, you can distribute. It can even be more than two factors, so long as it's just a multiplication of factors underneath the square root, right? Then you can distribute that square root over all of the all of the factors underneath the square root. Okay. The second one that we're going to need is the one that helps us to move in between fractional exponents and your radical, right? And that works like this. Okay, so this radical, right? Remember that if we have the square root, okay, then this value of m is an invisible 2. Okay, so we can write it in over here if we wanted to, right? So for all of these square roots, we know that we have an invisible 2 laying over here. Okay, so that acts as our m value. Okay, then if what you have underneath the radical, right, is some base to some power, okay, then that m value can come in underneath and actually become the denominator of your new exponent, which is made up of a fraction now. Okay, so you can see we have an exponent here on the base x, and we also have the same exponent there on the base x. Okay, and over here on the space x, we have an invisible exponent of 1 that we can write in. Okay, so taking this step by step, right, what we can do to simplify this is to first apply this law over here. Okay, so what we're going to do, we're going to distribute the square root over both of these factors in the numerator. Okay, so this is going to look like this. We're going to have the square root, right, and I'm going to keep that 2, okay, of 16 times the square root of x to the 7, okay, minus the square root of 25 times the square root of x to the exponent 7, okay, and all of this is going to be divided by the square root of x to the exponent of 1. Okay, alright, so there we go. Right, so you could have just opted to write the ones with the numbers, okay, as just the normal way of writing out the square root with that implicit 2, right? So implicit means invisible. Okay, right, so now from here we are going to move on, okay, to we're doing a lot of things at the same time. Okay, we are evaluating these square roots, these two. Okay, remember that when you're evaluating a square root, okay, or an even root, then you're considering the positive base that makes that even root true, right? And then at the same time, we're going to now apply the second property that we have written down over here. Okay, so we're going to rearrange these surds, right, to the square root of x to the exponent 7, right, to have this form over here where you have a fraction as your exponent. Okay, so what is the square root of 16? We all know that is 4. Okay, we need to times that by a base x to a new exponent of 7 over 2. Okay, so this value of m just comes in underneath and becomes your denominator. Right. Now you have minus the square root of 25, we all know is just 5. okay, times x to the exponent 7 over 2. Alright, now this is divided by x to the exponent 1 over 2. Right. Okay, so moving on from here, right, what we have is these two terms. Okay, we have a minus sign in between, which means that we have two terms. These two terms, luckily for us, are actually like terms, okay, because they have the same, right, base x to the exponent 7 over 2, right. So what's happening here? You have 4 of these factors minus 5 of them, okay, leaving you with minus, okay, x to the exponent 7 over 4. Sorry, 7 over 2. Okay, let's just try writing that 2 nicely. Okay, like that. And now this is now divided by x to the exponent 1/2. Okay, so now we have this negative on the outside, right? And we have this same base x. Okay, so now this brings us to our exponential laws, right? We have the same base and we are dividing, so which means that we are allowed to subtract the exponents. So, right, so we're going to have the exponent 7 over 2 minus the exponent 1 over 2, okay, which is going to give us negative out front. Then we have x, new exponent. The bases are the same here in our fraction, so we can just evaluate the numerators. So we have 7 minus 1, which is 6, right, divided by 2, okay, which is going to give us negative x. And we can still simplify this, right? 6 divided by 2 is 3. Okay, so that simplifies to negative x cubed, and you're done. Next question, right? Simultaneous equations. Okay, we need to solve for x, right? So in this case, we are basically actually now more actually solving simultaneously for x and y. Right? So ignore this instruction here at the top. Okay, we have a first equation. X times y is equals to 9, right? We should recognize this as a hyperbola, right? Because this is just y is equals to 9 over x. Okay, and then we also have x minus 2y minus 3. This is a straight line, okay? We'll just keep it like that. X minus 2y minus 3 equal to 0, okay? We'll call this our equation number 1. And we'll call this equation number 2. Alright, so what do we have over here, right? We have a hyperbola and a straight line, and we want to find out where do those two graphs intersect each other. Okay, so now that we've set out for ourselves in a first equation and a second equation, right, and I've done this deliberately, okay, because I can now see I can do a very simple substitution, okay, of y, okay, in the second equation. There's a y over there. Okay, so I'll go for that route. So I'm going to say substitute equation number 1 into equation number 2. Okay, so that's going to give us x minus 2 times y, in this case is now 9 over x, minus 3, and this is equals to 0. Okay, so when we simplify this, we'll have x, right, minus 2 times 9, okay, is going to be a minus 18. And this is still divided by x, and you still have the minus 3 equal to 0. Right, now what we're going to do is we're going to multiply through over here, okay, by the variable x. Okay, why am I choosing to multiply through by the variable x? Right, I want to flatten, okay, this fraction over here, right, and I know that even if I do that, I'm just going to end up with a quadratic, and that's something that I'm able to deal with. Okay, so if you multiply through by the variable x, you're going to have x squared, right, for this first term. Then you're going to have minus 18, because then the x's cancel out over there. Then you're going to have minus 3x, and that's equals to 0. Right, we can rearrange this if we want to, just to put it in the form that we are used to. Okay, and now we need to factorize this. Okay, so if we think of 18, right, and we're thinking of the factors of 18, I think the one that's going to work over here to get us to a middle term of 3 is 6 and 3, right? So we're going to have x over there and an x over here, right? And then we're going to have 6 and 3. Okay, so 6 and 3 is going to give us 18, right? We know that we need a negative, so we're going to have different signs over here, right? But then those different signs have to be such that we get negative 3x as our middle term, right? So how is that going to work? It's going to work out if we have negative 6, right, plus 3. All right, so from there, okay, we get that our first solution is going to be given by x minus 6 is equals to 0, or when x plus 3 is equals to 0, giving us that, that x is equals to 6 and x is equals to minus 3. Right, so that's our x values. Right, now we need the corresponding y values, because at the end of the day, these are points of intersection, right? So points are made up of an x and a y value. Okay. Now what we're going to say is we're going to substitute the values of x, so values of x, okay, into equation number 1. Okay. So you can show that substitution. So y is equals to 9 over x, in this case is 6, or you have y is equals to 9 over x, which in this case is negative 3. I can just pull that negative out to the side over there and put the 3 underneath. Okay. So these ones will simplify. Okay, so 3 goes in here 3 times, right, and in here twice. Okay, and you also have y is equals to negative, right? 3 goes into itself once, into 9 3 times, so it's 3. Okay. And then if you want to, you can put this as a final step. I can say therefore, okay, when x is equals to 6, y is equals to 3 over 2, and when x is equals to negative 3, y is equals to negative 3. Right, so that's one way to do it, okay? So writing it out in words. Another way would be to just give it as a coordinate. So 6, 3 over 2, and minus 3, minus 3. Okay. Okay, so if we just get a visual sense of our solutions, right, if you just quickly sketch this out, it means that you are going to have 2 points of intersection between your hyperbola, right, and these 2 straight lines. Okay, these 2 straight lines are going to have different equations to this one. Okay, I'm sure if you add them, you'll get this equation over here. Right, but basically these ones are going to have their own individual equations, and they're going to be defined by equations of straight lines passing through these points. Okay, but basically this is what we just solved for, right? We solved for these points of intersections between the hyperbola and straight lines. Okay. Moving on to the last question in this section, right? So question 1.4, we are asked to prove that x squared plus 2xy plus 2y squared cannot be negative, right, for any given x and y an element of real numbers. Okay, so if they are elements of real numbers, it means that they can take both negative and positive numbers, right? Because the integers is a subset of real numbers. Okay. Now, if we have to prove that this whole thing, okay, can never be negative, it means that it has to be made up of square numbers, okay? And really, this is one of those higher grade questions, but it all just boils down to identifying this factor over here, right? So that factor of 2xy, right, you should realize by now that that factor will come up, right, if you have a binomial, right, squared, right. So if you have, let me just fix my options here, right. So if you have x plus y, okay, which is essentially equivalent to just the binomial x plus y all squared. Okay, so if we just think of it in this form over here where we've written out the two factors separately, okay, then you know that you're going to have an x squared, right? Then you're going to have an xy plus an xy, which is the 2xy. Okay, so this, right, is that factor there that we see. Okay, and then you're going to have plus y squared. Okay, so now if you look at this, right, and you compare it to what you have, right, you have this 2y squared over here, right, so you can break this into just y squared plus y squared if you wanted to, right, so you're going to have x squared plus 2xy plus 2y squared, right? This is the same as saying x squared plus 2xy plus y squared plus y squared, right? Now, this part up until here, okay, is what we realize or we are familiar with from just basic algebra of just multiplying out these two brackets, x plus y, okay? Then, because we know that, we can make a substitution of this as just that binomial squared, right? So if we recognize that this can collapse down to this part over there, right? So just x plus y all squared, and then you still have that plus y squared, right? Then because you have a sum of two square numbers, and square numbers can never be negative, right? So then therefore x squared plus 2xy plus 2y squared is always greater than 0 for x, y, an element of real numbers. Okay, you can put a reason if you want to. Since x plus y all squared is always going to be greater than 0, and y squared is also greater than 0 all the time, right? It's actually greater than or equal to 0. Okay, so this all just boiled down to identifying this factor 2xy that we've come across before, right, in earlier grades. Okay. Okay, so now we've reached question number 2, right, of this paper, right, and let's just see what it says. We are given a quadratic sequence, right? So we don't have to wonder what type of sequence this is. We are told that this is a quadratic sequence, right? Or a quadratic pattern. Okay, and this quadratic pattern is made up of terms 5, 10, 17, and 26. Right? The first question wants you to write down, okay, the next two terms of the pattern. Right? So for this, unfortunately, you still have to evaluate your first difference, second difference, and all of that, and just work backwards. Okay, so we want to put a number there and a number there. Right, so if we evaluate first differences, okay, we're going to have 10 minus 5, which is going to be 5. Then we're going to have 17 minus 10, which is going to be 7. Then we're going to have 26 minus 17, which is going to be 9. Right, and we'll stop there, go for the second difference. Right, so 7 minus 5 is 2, right, and then 9 minus 7 is also 2, sorry. Okay, so now working backwards, right, so when we went this direction, we'll try and indicate it. Okay, so when we went this direction, right, we were subtracting. We were saying 9 minus 7 is 2. Okay, so now what we want to do is work in the opposite direction. Right, we want to now work in this direction. So if we work in the opposite direction, we're now adding. Okay, so 7 plus 2 is 9. Okay, so we're going to use that to generate the other terms. Okay, so going from here, we know that if we have 9 over here, we need to grab hold of a 2. Okay, so 9 plus 2 will be 11 over there. Same thing over here, we need to grab hold of this, right? So 26 plus the 11 will give us the next term here, which is the 37. Right? This is what we're required to find. Okay, then we go back down and we do it again, right? So from the 11, we need to grab hold of a 2 to get the next term here, which is going to be 13. And then the 37 is to grab hold of the 13 to give us the next term of 50 over there. Okay, so then to finalize this, oopsie, right? So to finalize this, you would then therefore say, therefore, okay, how many terms do we have so far? 1, 2, 3, 4. Right, so you would say term 5 and term 6. Right, that's the next two terms. Term 5 is 37 and term 6 is 15. Okay, so next question, right, question 2.1.2, we want to determine the formula for the nth term, right, of the pattern. Okay, so the nth term, remember, is the formula that will generate any one of the terms in this pattern. Okay, so we have to just recall back that analysis that we did. Okay, so this analysis, right, why do we need to recall this analysis back? Well, because we need to grab hold of these values, right? So our A value, our first term of the first difference, and our first term. Okay, right. So we have to use those to get to the nth term. Okay. So when we do that, we know that we're going to have this as 2a. Right? So this is 2a. That is going to be 3a plus b, this value, and this is going to be a plus b plus c. Okay, that value. Right. So going for that, we're now going to solve all of these equations. Right. So we have, wow. Right. So we have 2a is equals to 2. Therefore, a is equals to 1. Next equation, 3a plus b must equal 5. Right. If you substitute a is 1, you will just get 3 plus b is equals to 5. Therefore, b must equal 5 minus 3, which is 2. Okay, next equation, a plus b plus c must equal 5. A is 1, b is 2. Okay, that gives us 3 over there. We have plus c over here. All of this is equals to 5. Okay, so then therefore c must equal 5 minus 3, which is 2. Okay, so we have these three values. Okay, but now we need to answer the question. The question asked us for the n term, not for the values of a, b, and c. So we have to conclude and say, therefore, right, the n term, which is denoted by Tn, is going to be given by the a value, so that's 1, so it's just n squared, right, plus 2n plus 2. Okay, so that's the n term. Question 2.1.3, right? We are now asked which term, right, of the pattern will have the specific value 1765, right? So to do this, we need to pull up the general term that we just calculated, right? So there it is. Okay, let me just erase this. So a lot of students still struggle with figuring out whether they're calculating n or they're calculating Tn. Okay, so just use one of these numbers that you already know. Okay, if you were looking for which term, right, had the value of 10, okay, then you would definitely say it's term 2. Okay, so what did you solve for? You solved for that n over there. Okay, so which means that what you are given is a value, right? So Tn, because you don't know what that n must be. Okay, so this must go over here, 1765, and you now need to solve for that n, right? Just like you knew the n over there. Okay, so then we have n squared plus 2n plus 2. Right, so setting this equal to 0 on one side, because we have quadratic to solve, we're going to have n squared plus 2n, right? Now we have 2 minus 1765, which is going to give us minus 1763. Okay, most definitely will not try to factorize this into two factors. So I'm going to immediately go into the quadratic formula and redefine it for n. Right, so n is now going to be equals to minus b plus or minus the square root of b squared minus 4 times a times c divided by 2a. Okay, identifying all of our a, b, and c values, we get that a is 1, right? It's invisible over there. B is going to be 2, and C is going to be this minus 1763. Okay, so substituting all of that, let's just write in that invisible 1 over here. Okay, so when we substitute that, we're going to have minus 2 plus or minus the square root of 2 squared minus 4 times 1. So times minus 1763, all of this divided by 2 times 1. Okay, so then therefore n is going to be some value, or n is going to be some value, but we're going to have to reject one of them, because we know that n in this case is representing the number of terms. Can definitely, or I know from experience, right, that one of these values of n is going to work out as a negative number, and we're going to reject that negative number. Okay, so evaluating this in the calculator, right, we're going to have that therefore n must equal 41, right, and you're going to reject that negative n, right? Because n in this case represents the number of terms, right? So what we are really saying over here, just like how we said in the beginning, that term 2 has a value of 10, right? What we have now calculated is that term 41 has a value of 1765. Okay. Okay, question 2.2, right? We are given that the first 24 terms, right, of an arithmetic sequence, okay, are these values over here. Okay, so sorry, arithmetic series, right? So they're the values 35, 42, 49, all the way up to 196. Okay, so since these are the first 24 terms, we know that this is term 24 and it has a value of 196, right? This is term 1, and we also call term 1 A. Okay, so the two variables A and term 1, right, mean the same thing. Okay, now the question is to calculate the sum of all natural numbers, right, from 35 to 196, right, that are not divisible by 7. Okay, now if we look at this sequence given to us, right, if we calculate the common difference over here, right, you get that the common difference is 7, right? So which means that this series given to us is a series of numbers that are divisible by 7, okay? Because if the common difference is 7, then they are all increasing, or they are all basically multiples of 7, right? So now because these numbers are multiples of 7, they are actually divisible by 7, okay? So we can say, okay, so we're going to move from the series and we're just going to talk about the sequence, right? So the sequence of numbers, okay, 35, 42, 49, all the way up to 196, right, is divisible there by 7. Okay, and this sequence we know contains 24 terms, right? Now the sum, okay, or the number of terms, let's do that. So the number of terms in the sequence of numbers not, right, divisible by 7, okay, that is going to equal, okay, the total number of terms from 35 to 196, okay, based on the natural numbers, right? So we need to calculate that, and then we need to subtract from that these 24 terms that we know are divisible by 7, and we're going to get an answer. Okay, so let's go for that. Right, so when we're looking at the natural numbers from 35, right, we're looking at the sequence 35, 36, 37, all the way up to 196. Right, so this is Tn, this is now T1. Okay, so because we don't know how far this goes, so it becomes Tn, right? So we now again want to calculate this n, right? So Tn is going to be equals to, well, what is the formula over here? Well, the common difference is 1. That's because we're dealing with natural numbers. Okay, so the formula is going to be A plus n minus 1, right, times d, which in this case is 1. Okay, so we're going to have that Tn is going to be equals to 35 plus, if we distribute this, you're still going to have n minus 1. Okay. We can now substitute Tn as 196 equals to, we have n, then we have 35 minus 1, which is going to be plus 34. Okay, so then the number of terms in this sequence of natural numbers from 35 to 196 is 196 minus 34, okay, which is 162. Right, so now we're going to put that 162 here. So 162 minus 24, okay, that gives us 138 terms, right, that are not divisible by 7. Okay. Okay, so now let's check what we've calculated so far. So we looked at all the natural numbers from 35 to 196, and we calculated that there's 162 terms in total, right, for that whole sequence. Okay, why did we have to calculate this number? Well, I calculated this so that I can evaluate the number of terms, right, in the sequence of natural numbers that are not, okay, divisible by 7. Okay, so that's the total terms, okay, minus the 24 terms in this sequence that is divisible by 7. So that gives me 138 terms that are not divisible by 7. Okay, so now because we are looking for the sum, okay, of all the natural numbers that are not divisible by 7, I can now say that Sn, right, where n is these 138 terms that are not divisible by 7, okay, and I'm going to use the formula n over 2 into a plus L, okay, where L is going to be the last term that is not divisible by 7. It's just going to be the number before this, right? It's going to be 195. Okay, that's the last term that's not going to be divisible by 7. Okay, so substituting all of this, that's our n value, 138 terms divided by 2. First term not divisible by 7 is going to be this term right over here. That 36 is not divisible by 7, and that's the last term not divisible by 7, 195. Okay, so plugging that into your calculator. Okay, so plugging that into the calculator, you get that this works out to be 15,939. Okay, so that is the sum, okay, of all the natural numbers between 35 and 196 that are specifically not divisible by 7. Okay. Alright, question number 3. We are told that there is a gentleman called Temba, right, who is planning a bicycle trip from Cape Town to Pretoria. The total distance covered during the trip will be 1,500 kilometers. Okay. He plans to travel 100 kilometers on the first day. Okay. And then after that, for every following day, right, he plans to cover 94% of the distance he covered in the previous day. Right. Okay, so question 3.1 is asking what distance will he cover, okay, on day 3 of the trip. Right. Now, basically, we just need to write out the term, okay, the third term of the, you can call it a series, right, because we're going to be adding up all of these distances and they're all going to equate to a total distance of 1,500 kilometers, right? Now, if we read this question properly, it says, what distance will he cover on, right? So we're not asked what distance did he cover over the 3 days, right? But rather specifically just on day number 3. Okay. Now, in order to do this, right, what I'm going to do just to make the solution make sense for me is I'm going to reassign, okay, so reassign the variable t, okay, to be the variable, okay, d, right, where d represents a day, right. Let's just fix that. Represents day. Okay, so if I am looking at, maybe let me write out the series so that you can see what I'm talking about here. Okay, so the first term of his series, right, so day number 1, okay, he plans to travel a total of 100 kilometers, right. Then we're going to add to this the distance that he's going to travel on the second day, right, and he says that for every following day, he's planning to cover 94% of the distance he covered the previous day, right? So what's the distance he covered the previous day? It's 100, right? So he's planning to cover 100 times 0.94, right, of that distance, okay? Now, what's going to happen on day number 3, right, which is basically the answer to this question, right? He's going to cover 94% of this distance that he covered on day number 2, right? So then you're going to have 100 times 94% times 94% again, which is the same thing as just writing it as 100 times 0.94 squared, okay? Right, so then therefore, right, the distance covered on day 3, right, will equal 100 times 0.94 all of this squared, okay? So if you plug that into the calculator, right, you get a value of 88, right, 0.36 kilometers. Okay, remember we were given the units over there. Okay. Right, next question. 3.2, we are asked on which day, right, of his trip will Timber pass the halfway point. Okay, so now the halfway point is going to be when he has a cumulative distance, right? And I mean, when I mean cumulative, I know I'm using a statistics word here, but basically he's saying the sum of all his distances up to that point. Okay, so if he has to go to the halfway point, right, then he has to cover half his total distance, right, which is going to be 750, okay? So we need to take the sum of a specific number of distances, okay? Which distances am I talking about? Let me just go fetch them. Right, so remember in the previous question, we determined that the first 3 terms, right, of his specific series, right, it's going to carry on, okay, up until some term, okay. These terms over here, okay, are going to accumulate, right, up until some point d something, right, dn, okay, where Sn is going to be 750. Okay, right. So now we can see very clearly, right, that what we have over here is a geometric series, right? And if we just quickly identify our components, right, we have an R of 0.94, okay, that's our R value. And we have an A value of 100. Okay, that's our A value. Okay, so once we've identified those two components, we can just substitute them into the Sn formula for a geometric series, right? So that's going to be A, right, into the R value to some exponent, right, minus 1 divided by R minus 1. Okay, so we'll substitute 100 for the first term. Okay, we know that our common ratio, right, is 0.94. This is to some exponent n, right, where n is going to tell us the day, right, that he's going to reach this halfway point. Okay, minus 1 divided by 0.94 minus 1. Okay. Right. So 750 times 0.94 minus 1, okay, that gives you minus 45 on this side, okay. Then we can divide that by 100, right. This is going to equal 0.94 to the exponent of n minus 1, right. Now we can take the minus 45 divided by 100 and add 1 to that, right, and we get 11 over 20 on the left hand side. That's going to equal 0.94 to the exponent of n, right. Now we want to solve for this n, so we're going to need to use logarithms, right. So we are just going to say log of this base 0.94 of 11 over 20, okay, that's going to equal the value of n, right. N works out to be, if we write it to two decimal places, we get 9.66, okay. Now because this will round up, right, so obviously it will happen after the 9th day, right, so we'll just round it up to the nearest whole number, okay, and conclude that therefore timber passes the halfway point okay, on day number 10, okay, or the 10th day if you want to write it like that, right. Right, question 3.3, right, we are now told that timber must cover a certain percentage of the previous day's distance to ensure that he eventually reaches Pretoria. Right, now we have to calculate, all the possible values of this percentage, right. So if we just look at what's going on here now, right, in the beginning we were told Timber's plan, right, so he was planning to cover 94%, right, of the previous distance for every single day until he gets to Pretoria, right. I don't think that's very realistic of him, right, because chances are he won't cover exactly 94%, okay, of the previous distance every single day. He could, you never know, right. But now what this question is trying to say, right, is for us to calculate all the possible percentages that he can cover, right, or that are necessary for him to cover so that he eventually reaches his destination, right. So now notice, where did this 94% go, right? When we wrote out the series, right, 94% went over here, okay? So which means that we basically need to calculate all these possible values, right, of this position here, right, this position of 0.94, and we already identified that this is the R value, right, of our geometric series, right. So we now just need to calculate all the possible values of R that he can have, right, so that he eventually gets to Pretoria. Right, now we were given that his total is n, right, which we can sort of like take it as his sum to infinity, right. That was 1,500 kilometers, right. That's the distance between Cape Town and Pretoria, right. Now we know that the sum to infinity, and I'm going to use this one, okay, because our R value is between -1 and 1, okay, right. Then we have A divided by 1 minus R, right? We now have 1,500 here, okay? The A value is 100, right? Let's say that he is dedicated enough to commit to covering that total 100 kilometers for the first day, right? Now we want to calculate the possible R's, right, which is basically the percentages that he can cover for the subsequent days, right? So just solving for this, multiplying both sides by 1 minus R, we'll get 1,500 minus 1,500 R is equals to 100. So then minus 1,500 R is going to be equals to minus 1,400. So then R is going to be, right, so the negatives will cancel out. We'll have 1,400 divided by 1,500. Okay, and the zeros basically cancel out, right, leaving us with a simplified ratio of R being 14 over 15. Right, so then now it means that right, let's evaluate what is this, right, as a percentage. Okay, so 14 over 15 times 100, okay, that is 93.33%, right? Okay, so basically what we're saying with this question is that he doesn't have to be so strict on himself and stick, right, to his rigid plan of covering exactly 94% of his previous distance. He can sometimes cover 96% and then 97 and then back to 94 and then again maybe move it up to 99% if he can, right? Probably the 99% is going to be like on his last stretch or something like that, right? Right, so now we've reached question number 4. Okay, and now that we start seeing graphs, it means that we have finished with the section of equations, inequalities, and exponents, and all of that. And we've also finished with the section of sequences and series. Right, so now we are in the section of graphs and graph interpretation. Okay, all right. We have over here, right, a logarithmic function that has been plotted for us, right? Okay, there's a little bit of a mistake in this question in terms of that this point, okay, is not on the graph exactly. Don't know what happened over there, right? But this point is supposed to be exactly on the graph. Let's see if I can paint over it. Okay, there we go, so that it doesn't distract us. Okay, so what do we have over here? We have that the graph of the function, right, log base 4 over 3 of x is drawn, right, and this point B, which has the coordinates 16 over 9p, right, is a point on the graph of f, right. Now with that said, the first question is asking us for which value, right, or values of x is this function, right, so we can just replace that as f of x. Okay, when is that less than or equal to 0, right? So we can go back to the sketch. It's quite a simple graph interpretation question at this point, right? Again, we go through the same analysis that we spoke about. This x-axis, right, is represented by the line y is equal to 0, okay, and above, right, this region above is y greater than 0, and below we have y less than 0. Okay, so we were looking for where is this function, right, less than or equal to 0, right? So basically we are interested in when does it cover this region here below the x-axis, right? Okay, so we're going to have an open circle here, right, because we know that this line, right, x is equals to 0, or the y-axis, right, that is a vertical asymptote for our graph, right? So that means that we are not including this value of 0. Okay, so we have an open circle there, and then we're going to be looking at all these values here in between, right, until we get to the x value there at the x-intercept, right? So which means that our task remains now to determine this x value here at the x-intercept, because that is included in our solution. Okay, so that is our desired x values. Right, all of these ones shaded in red, including that one over there. Okay, so basically we've now just determined that we have an x-intercept at a value of 1. Right, so then therefore, okay, log base 4 over 3 of x, right, is less than or equal to 0 when, okay, x, right, is going to be strictly greater than 0 but less than or equal to the value of 1. Okay. Right, question 4.2 now says to determine the value of p without the use of a calculator. Right, so now remember that the value of p is this y value here at this point, right, on the graph of f. Right, so we have that f of x, right, is defined by the equation log base 4 over 3 of x, right. What we're going to do now is to substitute the point b, which is 16 over 9, y value of, what is it, p? Yeah. Let's just move it out the way a little bit. Okay, so this is going to be our y value, so that's basically the f of x, right? So that's p. Keeps looking like a 9 to me, sorry. Right, so we have p is going to equal log base 4 over 3, right, and the x value is 16 over 9. Okay, so they wanted us to evaluate this without the use of a calculator, because you can see that you can clearly just plug all of this into the calculator. Right? The reason why they want us to do that is because they want us to show the step where we reshuffle all of this. Okay, so if we do that, right, it's the same thing as what we did in the previous step, right? The base is always the same. The base is 4 over 3, right? So the base to the exponent of p, right, is equals to what's inside of the log, right? So 16 over 9. Okay, right. Now we can write 16 over 9 using base 4 and base 3, right? So we have 4 over 3 to an exponent of p, and we can rewrite this as 4, right, squared divided by 3 squared, right? And basically we can pull that squared out from those two bases like that. Okay, because then this square just basically distributes to both of the bases in the numerator and the denominator, right? Then you still have your 4 over 3 to the exponent of p that side, right? So now we have same bases. Okay, now because we now have same bases, right, we can equate the exponents, right? So then therefore p is equals to the value of 2. Okay. Okay, question 4.3 says write down the equation of the inverse of f right, in the form y equals, right. So we have f of x is equals to log base 4 over 3 of x, right. So we're going to say let f of x equal y. Okay, so then y is equals to log base 4 over 3 of x. Okay, now what we're going to do is we're going to swap the x and y around. Okay, so when we do that, we're going to have x is equals to log base 4 over 3 of y, right? And now we need to solve for y. Okay? So if we solve for y over here, we are basically just moving into exponential form. So we're going to have the base 4 over 3, right, to the exponent of x is equals to y. Okay, question 4.4 says write down the range, right, of y is equals to f inverse of x, right. So this is the equation that we just determined, right. We want to write down the range of the equation 4 over 3 to the exponent of x is equals to y. Okay, now we know that this is an exponential function, right. It doesn't have any shifts on it, no horizontal shift, no vertical shift, right. So basically it just lies asymptote, right, to the line y is equals to 0, right. So therefore its range is all the y values greater than 0. Okay. Okay, so if we just go up to the sketch and just illustrate what we were just talking about, if you need to see the pictures, that is our line of reflection, okay, for the inverse function y is equals to x. Okay, so let me just extend these lines. Okay, so when we reflect, right, this logarithmic function, what we're going to get is an exponential function that look like this. Okay, and it's going to have the line y is equals to 0, okay, which is basically the x-axis as its asymptote, right. So basically its range is all these y values that it can take, right, and it can't take, the only y value it can't take is this y value here at the x-axis, right. So this y value is 0. This is the only y value that it can take, right. So this is an asymptote, horizontal asymptote, right, and we're basically talking about all the y values above 0. That is the range of our exponential function. Okay, so question 4.5, right, it says that the function h of x is equals to 3 over 4x is obtained after applying two reflections on f, right. So remember that f is our logarithmic function. We now need to write down the coordinates of b double prime, right, which is the image of b on the graph of h, right. So in order to do this, we'll just go back to the sketch that we developed. Okay, now we can see that we have actually pulled off one of the reflections. Okay, so we can actually say that one of the reflections is the reflection about the line y is equals to x, right. So going from the logarithmic function to its inverse, right, which is the exponential, right. So we can say that this is reflection number 1. Okay, now obviously if we reflect that, then the point B will end up being somewhere here, and it will have the coordinates 2, right, 16 over 9. Okay, that's just swapping the x and y coordinates around over here, right? Now we were told that the graph of h, right, so h of x, is given by the equation 3 over 4 to an exponent of x. Right, so now this base has just been swapped around. We can easily swap this base around, okay, if we just write this as h of x is equals to 4 over 3 to an exponent of negative x. Right, now if you have negative x, right, that represents a reflection about the y-axis. Okay, right, so if we take this blue graph and we now reflect it about the y-axis, right, this point will sort of be like a pivot point, right, and we will just have this flipping around like this. Okay, so we're going to go from having b being greater than 1 to now b being greater than 1, sorry, less than 1 but greater than 0, right? So we're going from having an increasing exponential function to a decreasing exponential function, right? So now if we trace b, right, so this is the coordinate of b prime, right? Now if we trace it, okay, in other words, we trace where it's going to go after this reflection about the y-axis. Okay, it's going to go somewhere there, right? And even if the sketch is not accurate, right, we can see that b double prime is going to keep its y value constant as 16 over 9. Okay, it's going to keep that y value constant, right? Now it all boils down to figuring out what is the x value, right, at this point. Okay, so what's the x value over there, right, which gives this y value of 16 over 9. Okay, we can easily calculate that by just substituting into the formula. Okay, so when we do our little side calculation, we have that h of x, right, is equals to 3 over 4 to the exponent of x. Okay, but we already spoke about this is equivalent, right, to talking about h of x as being 4 over 3 to the exponent minus x. Okay, we spoke about that above, right? Now I'm going to substitute this y value, right, that we saw, which is 16 over 9, and that must equal the base 4 over 3 to the exponent negative x. Okay, now we saw that 16 over 9 is 4 over 3 all squared. And we still have 4 over 3 this side. Right, same thing, bases are the same, so then therefore negative x is equals to 2, so then therefore the x value at this coordinate must be minus 2. Okay, and this is the only thing that you would report. So on your answer sheet, you would just write b double prime, okay, and give the coordinates negative 2, 16 over 9, and that's it. Okay. Moving on to question number 5, okay. So we are now into the section of functions and graph interpretation, okay. What we have over here is a hyperbola and a parabola, okay. So the hyperbola is this function f of x and the parabola is the function g, okay. Now quickly before we carry on, I just want to change the function of f of x into the general form f of x is equals to a divided by x minus p plus q. Right. Why do I want to change it to look exactly like this? Well, because this general form helps you to look at the equation of the hyperbola and immediately identify the correct p and q values. Right. So for me, I feel like it helps you to not make mistakes. Okay. So if we change f of x to look like this, basically the objective is to get a negative there in the denominator, right? So we're going to have f of x is equals to 2 divided by x minus 1. Okay, and we still have that plus 4, right? Now that we have the equation in that form, right, we can immediately tell now that we have a vertical asymptote through the point -1, okay, and we have a horizontal asymptote through the point y is equals to 4, okay. So we can now go to the graph and easily identify those lines, okay. So you can see on the graph, right, there it is quite clearly. You can now see that this vertical line is going to be described by the equation x is equals to -1, and this horizontal line is going to be described by the equation y is equals to 4. Okay, so going back to the given information, we are told that C, which is the turning point of the graph of G, this lies in the horizontal asymptote of F. Okay, that's a very interesting thing for them to say, right? Because some people will tend to forget that these asymptotes, right, are only really there for the hyperbola, okay? And they mean basically nothing for the parabola, right? So the parabola can cross any of these asymptotes if it has to, right? And it will actually. So if you see over here, for instance, this parabola does carry on for infinity. Maybe I'm over exaggerating it there, but let me just try again, right? So it will carry on downwards, and you can see that eventually it will cross this vertical asymptote, but that doesn't matter for the parabola because the vertical asymptote means nothing to the parabola. Okay? It's just going to carry on its journey downwards. Okay, so same thing over here. It just happens that what they're saying here is that the turning point, right, actually lies on that horizontal asymptote, right? And because we know that this is the point 4, right, they're basically giving us extra information here. So if this point lies on this line, okay, this horizontal line, we now know that the y value there at C, okay, is going to be a value of 4, right? So that's nice information to have. Going back up, right, we see that they say that the graph of G passes through the origin, okay, and we have this point B defined by the coordinates K, 14/3, right, and this is a point on F, right, such that BC is parallel to the y-axis, okay, so let's just see. So when we look at the sketch, right, we see the point B, right, and the point B, there's nothing special about it, it's just a point on the graph of F, right. Now, they're just saying that this distance BC, right, this vertical distance, right, this is parallel to the y-axis, right, so meaning that it's a straight vertical line, okay. Now, if it's a straight vertical line, then all of these x values are the same on it, right, so which means the x value over here, right, that's an x value of k, meaning that the x value here at C is also k, right? So now we know the coordinate at the turning point of this parabola in terms of k, right? It's k4, right? So that's half of our job done, right? All right, so with that said, let's go into the questions. Okay, 5.1 says we need to write down the domain of f, right? So remember that f is our hyperbola, right? And if we're looking at the domain of the hyperbola, we just want to see which x values can it take, right? And you can see it actually ranges through all the x values except for this specific x value here at its vertical asymptote, right? So that's the only x value that the hyperbola is not defined at. So when we write down our domain, we can just simply say that the domain of the function f, right, is going to be defined by, right, and we usually use set builder notation for the domain of our hyperbola because it's easier to write down. Okay, so we use these curly brackets and we write x, and then this vertical line means such that, right, x is an element of all the real numbers, right, but x cannot equal a value of -1, right? And of course, that's not the only way that you can state the domain, right? If you wanted to, you could use interval notation, that's fine. You could say that the domain of f, right, equals x, an element, right, of negative infinity to -1 together with -1 to positive infinity. Okay, so it's up to you how you state the domain of this function, whichever notation is more comfortable, right? Okay, question 5.2, right, we need to determine the x-intercept of the function f, right? So we're still working with the hyperbola. Right, so we have f of x given to us as 2 divided by x plus 1 plus 4, right? We want to determine the x-intercept, so you still have to write this down. I know it's irritating. Okay, so for x-intercept, right, we're going to set f of x equal to 0, right? So then therefore 0 is equal to 2 divided by x plus 1 plus 4, right? So when you move the plus 4 to the other side, you get -4. And this is equals to 2 divided by x plus 1. Will give us -4x minus 4 is equals to 2, right? So -4x, sorry, is equals to 2 plus 4, right, which is going to be 6. Okay, so now we can divide both sides by -4x, giving us x is equals to 6 divided by 4, and I'll just pull out that negative to the front. Okay, we can still simplify this fraction, and it will work out to 3 over 2. Sorry, -3 over 2. Okay, so let's just check on the graph that makes sense. Where's the x-intercept? Okay, there it is. Right, so if this is the line x is equals to -1, right, then this point being -3 over 2 makes sense because 3 over 2 is 1.5. Okay. Okay, question 5.3 says we need to calculate the value of k, right? Let's just go back to the function and see what is k. Alright, so k is defined as the x value here at b. Okay, so since b is a point on f, we can easily use the equation for f of x, right? And we are going to substitute that point b. Okay, so it's k 14 over 3. Let's just verify. Yes. Okay. Right. So basically what this is saying is that the f of k, right, is equals to 2 divided by k plus 1 plus 4, right? But we are given the value of f of k, it's 14 over 13. Okay, and that's equals to 2 divided by k plus 1 plus 4, right? So into your calculator, you will go 14 over 3 minus 4, and that will give you 2 over 3 here on the left hand side. This is equals to 2 divided by k plus 1, right? And now what we have is two fractions which are equal to each other, so we can apply the method of cross multiplication, and that will give us 2k plus 2, right, is equals to 6, right? So then therefore 2k is equals to 6 minus 2, which is going to be 4, right? Leaving us with k is equals to 2. Okay, so let's just go back up to the sketch, right? So we now know that this k value is 2, which means that the x value there is 2, right? So which means we also now know the coordinates here at C, right? Remember this was defined earlier on as k4, We now know what K is, so this is now the coordinate 2, 4. Right, so that's the coordinate at the turning point of our parabola. Right, question 5.4. They now want us to write the coordinates of C, right? And remember that C was the turning point of the parabola. We just spoke about it, so that is just the coordinate 2, 4. Okay. Next question 5.5. Determine the equation of G in the form y is equals to this, right? We all know this is the vertex form of the parabola, right? We know that this P and Q, right, that determines the position of your turning point, right? That's basically the coordinates of the turning point. So then, because we know the coordinates of the turning point, that is 2, 4, okay, we can easily substitute that into this form, right? So we have y is going to equal a into x, right? And it has to be minus 2 in the brackets, okay? It's one of those opposite sign issues, right? So if you see minus 2 in the bracket, you know that it's positive 2 on the outside, okay? All right, so now we need one other point on the parabola. We were told that it goes through the origin, so we can use the point 0, 0. Okay, so that will give us 0 is equals to a times 0 minus 2 squared. Sorry, I forgot to substitute the value of q there. Okay, value of q here is 4, right? We still have plus 4, right? So we have 0 is equals to 0 minus 2 in the bracket here is going to give us minus 2. Minus 2 squared is going to be a 4. So we have 4a minus plus 4, sorry. Moving this 4 to the other side, we get minus 4 is equals to 4a, right? Then obviously therefore a is equals to minus 1, right? So we can just go up to the sketch and make sure that an a value of minus 1 makes sense, right? It does make sense because you can see the parabola is facing downwards, right? Question 5.6, we need to now determine for which values of x will f of x divided by g of x be less than or equal to 0, right? So this is one of those graph interpretation questions, but for this one, it's not so easy as just having f of x less than 0 and then you conclude that you are basically just looking for where the graph is below the x-axis, right? Unfortunately for this one, we're going to have to go through a little bit of more analysis and sort of like a calculation. So we'll go back to the sketch, right, and we'll just remind ourselves, right, that the x-axis, right, is defined by the line y is equals to 0, right? So we will be interested in where any of these two graphs intersects this line, okay? And then we know that the area above is defined by y being greater than 0, and this area below, or the region below, is defined by y being less than 0. Okay, so if g is below, then it means that g of x is negative, right? And if f is low, then it means f is negative, and the other way around as well. Okay, so the way that you would go about this in exams, like you would take a ruler, right? I don't have a ruler with me in this little program. So your ruler would look something like that, right? And what you would do is you would slide your ruler along, okay, and just record what is happening to both the functions as you move along, right? Is the function above while the other one is below, or are they both above, both below, or what's happening, okay? And then we're going to take the overall sign, and in this case it's not a multiplication of those signs, but rather we want to divide the sign on f with the sign on g. Okay, so I'm just going to split this into different regions, right? So in other words, I'm going to use the method of using a ruler, right, sort of digitally, and break this into a few regions, right, for us to start analyzing. Okay. Okay, so I've now identified all the regions, okay, that you would actually have as you pass your ruler along, right, starting from the left hand side and moving your way to the right hand side. Okay, so now what we're going to do is we're going to do a quick analysis of each graph in each region, right? So starting in this first region, the green one, right? I hope you can see it on your screen. It's this light green region over here, and it stops right here, right, at the x-intercept of our hyperbola, right, which we determined before as the point minus 3/2, right? So when we work our way all the way up to this x-intercept, okay, we know that here, right, f is going to be 0, right? Now remember that we were asked to determine, okay, f of x divided by g of x, right? So if f of x is 0, right, then it satisfies this option here of equal to 0, right? The only thing we need to watch out for is g of x being 0, right? So we have to exclude all the x-intercepts of g of x, right? So whenever we meet an x-intercept of g of x, that's not going to be included, right? Because then you'll be dividing by 0, right? So from there, we now see, okay, in this green region, right, just before we got to this point, right, f of x is above the x-axis, right? So f of x is positive for this region, right? And remember that I said that we mustn't let these asymptotes trick us for the parabola, right? I tried to indicate here that the parabola is still going to carry on, right, on its journey. So if we try to extend these lines to help you, right, you can see that it's going to carry on downwards, and it's eventually going to be in that green region, right? But the point of the matter is that in this green region, right, wherever it is, how doesn't matter how low it is, right, below the x-axis, the point is it's below the x-axis, right? So for the green region, we'll just write it over here. G of x is negative, right? So now if we evaluate this fraction, right, f of x is positive, g of x is negative, so we have a positive divided by a negative. That's an overall negative region, right? And we'll just circle it to remind us that this isn't the sign that we are looking for, okay? Right, so now that we've identified one negative region, and that is also our desired case over here, right, less than 0, it means that we are taking all of these solutions, okay? So all of this is part of our solution set, okay? So all these x values less than negative 3/2, okay? Including that value there, right? We mustn't forget that. Alright, so now going into this reddish region, right, in between, okay, if I just extend over here, right, this is going to keep getting closer and closer to its vertical asymptote, right, but we can see that for these two graphs, right, they're now both below the x-axis, right, so there's the x-axis over there, right, okay, don't forget it. There's f of x, right? It's below the x-axis everywhere. There it is, there it is, there it is, there it is, right? And also g of x in this region, right? If we start from here, from the vertical asymptote, there it is, right? It's below the x-axis, right? So it's also negative, okay? So this is not going to work because negative divided by a negative is going to be a positive, right? So that's not a region that we are interested in, okay? The next region is going to start here at the vertical asymptote of -1, right? Because this is a vertical asymptote, we know that we can't include it, right? So we'll just put an open circle over there, okay? This region starts here and it ends here at the x-intercept, right, of g of x, right? Remember they said it passes through the origin, right? So it's there at the origin, okay? Now, remember I said we're going to ignore the x-intercepts of g of x because then we'll be dividing by 0, right? So we have an open circle here at the x-intercept of g of x as well, okay? Now, this region spans here in this gray area, right? Now, if you look for f of x, right, here's f of x. It's above its horizontal asymptote, right? But that's not what we're really focusing on. We are focusing on the fact that it's above the x-axis, right? So we just classify it as being positive for that region, okay? Now, in the same region, g of x is below the x-axis, right, for that little piece over there, right? So it's negative, okay? So again, we now have positive divided by negative, right, which gives this gray area, right, as a overall negative region, right? So we're going to be including this as our solution set, right? But it's all these values excluding the value -1 and the value of 0, okay? So the blue region starts here at x is equals to 0, right? And it's going to carry on up until we get to this x value here at the second x-intercept of g, right? I'm already going to just put an open circle there because I'm not going to include the x-intercept of g. Okay, so now in this blue region, you can see there is f of x, right? There it is, right above the x-axis, so it's positive, right? And what about g of x? Well, for this blue region, g of x is also above the x-axis. There it is, right? Can you see it, right? It's above the x-axis, so it's also positive, okay? Now, positive divided by positive is going to be a positive. So unfortunately, the blue region is also not our area of interest, okay? Now, onto the last region, right, this orange region over here, okay? We can see from this second x-intercept, right, we are just going to have to determine that value. It's quite easy to do it, right? We'll use symmetry. Okay, remember this is an x value of 0 here in this first x-intercept. The x value at the turning point is the axis of symmetry, right, of your parabola, okay? So it's 2 units away from this previous x-intercept, right, so 0, and then you used 2 units to get there, right? So it means that if you travel another 2 units, this will be an x-intercept at the value of 4, okay? So basically, we are now going to be looking at all the x values greater than 4, right? Let's just see. Okay, we were saying, right, f of x is above, right, the x-axis, so there it is, it's positive. And for all these x values greater than 4, there's g of x, right, it's below the x-axis, so it's negative, okay? Again, we have positive divided by negative, giving us this orange region as a negative region, right? So we have 3 solutions, right, to this desired inequality over here, right? So we are also taking all of these solutions, okay? All of these x values greater than 4, right? And strictly greater than 4, we're not including that x value of 4. Okay, so now that we've identified all of that, we are now in the position, okay, to write it down. Okay, so we're going to say, therefore, f of x divided by g of x, okay, is less than or equal to 0 when, okay, x is less than or equal to -3/2, right? That's that first solution over there. Or when x is just in between 0, sorry, other way around, in between -1 and 0, okay? So that solution set over there. And then we have this last one, or when x is just greater than 4, okay? You could write this in interval notation if you wanted to. It's not so difficult to do, right? So you'd say f of x divided by g of x is less than or equal to 0 when x is an element of negative infinity up until you get to -3/2, and remember that is included. Okay, union -1, 0, union 4 to positive infinity. Okay, so that was not so difficult of a question, but challenging if you don't know how to approach it. Okay. Question 5.7, right, we now need to use the graphs of f and g to determine the number of real roots, okay, of 2 divided by x minus 5 is equals to minus x minus 3 squared, minus 5, okay. We now need to give reasons for your answer, right, give reasons for your answer, okay. So we need to comment on the roots, right, of this equation, right, this one over here. Okay, and remember that roots also is represented by the term solutions, right? So we have two new equations over here, right? We have a hyperbola and we have a parabola again, right? And they are being set equals to each other. We know that whenever we set two equations equals to each other, right? We saw that in the beginning as well when we're doing the simultaneous equations, is that we're trying to determine how many points of intercept, right, or if any, do these two functions have, right? So if you have 2 points of intercept, then you have 2 real roots, right? 2 distinct real roots. If you have 1, you have equal roots, and if you have none, then you have no. In this case, we'll just say no real roots. Alright, so we have to basically compare, because they say use the graphs of f and g, right? So there's the graph of f and g, right? We are just going to, I think in this case, compare the equations of f and g to these equations that we're given now, right, and just see what happened, okay, to get to this point, right? So f was 2, okay, this was f of x, okay, it was 2 divided by x plus 1 plus 4, right? Now there's something that happened, right, in this position and that position, okay, for us to get to this equation over here, right? So it's basically transformations that they applied, right? Let's think about it, right? So to go from having a plus 1 to having a 0, right, it makes sense to then just add over here a minus 1, okay? Now, if we ignore this plus 1 and we just concentrate on this minus 1, if we saw a minus 1 there, we would understand that the graph shifted to the right, okay, by 1 unit. Right? Now, how did we get from 4, right, to a horizontal asymptote at minus 5? Well, 4 minus 9, okay, will get you to minus 5. Okay, so in other words, this graph of f has been shifted 9 units downwards. Okay, so if we just quickly sketch this for ourselves, okay, and if we trace that point B, right, remember this point B, okay, B was 2, okay, for K, so 214 over 3, right? So if we look at the Y values, right, it's going to move from a Y value of 14 over 3. We're going to minus 9 from that, so it's going to move to a Y value of minus 13 over 3, which is approximately minus 4 recurring, right? So it's moving down. If this is minus 5, it's moved down to a minus 4 recurring, so something around there. Okay, and then obviously I'll call it B prime, right? The x value, right, is now going to shift 1 unit to the right. So it used to be an x value of 2, so this is now actually an x value of 3. Okay, so it's 3 negative 13 over 3. Okay, that's now the new coordinate of B, right? Now let's look at what happened to g of x. Okay, g of x is equals to, oh, did we actually find the equation of g of x? Let me just go back. We made a little bit of a mistake here. Right, so going back to question 5.5, right, they wanted us to determine the equation of G in this form, and I just ended at determining the A value. Sorry about that. Don't make that mistake. Okay, so we now have that G, right, in this question they just wanted us to write it in the form y equals, so therefore y will equal the A value of -1. I'm not going to write the 1. Okay, then we have x minus 2 all squared plus 4. Right. So this is the equation of G. Okay, so going back here, I'm going to write it as as g of x. Okay, so minus x into, what am I saying? Minus x minus 2 squared plus 4. Okay, so if we compare it to this one, the A value is still a minus, right? So it's still facing downwards. And now we have something happened in here. Okay, let's just make some space. Right. So something happened in this bracket to move us from a turning point at 2, right, to a turning point at 3, right? So how do you move from a turning point at an x value of 2 to an x value of 3? Well, you just move 1 unit to the right, right? So there's a -1 here, okay? Opposite signs, okay? So 1 unit to the right, okay? And then we already saw from here that +4 minus 9, okay, will give you this -5. So the parabola has also been shifted 9 units downwards. Okay, so it's going to have its new turning point at the coordinates 3, right? So there's 3, that's 3. So 3 minus 5, okay, so it still lies on this horizontal asymptote. That will be C prime, okay, and it's going to look something like this. Okay, so there is a new sketch of this function, right? So these two, right, are now represented in the sketch over here, right? So when we look at this, right, we see that they only have one point of intersection between the two of them, okay? That's that point right over there. Okay, they only intersect over there, okay? So in other words, what they have is one real root, okay? Use the graph of f and g to determine a number of, okay, so we're going to say therefore, and they didn't name these functions, so we'll just say 2 over x minus 5 equal to minus x minus 3 all squared minus 5 has one real root. Okay, and we had to give a reason for our answer, right? And this is because there is one point of intersection between the two graphs. I want to add over here, let me say transformed graphs. Basically, the number of roots, right, will tell you how many intersections you're going to have, right? Because, and it works both ways, right? So if we had two intersections, right, between these two functions, then we would say that they have two distinct real roots, okay, because they would obviously be in two different places, okay. You could have also used over here equal roots, right, but because there was this term number, right, that's why I opted to just say 1, okay, just to give an answer to this, right, number. Okay, so we just say 1 real root. Okay, and the other option that could have happened is that these two functions wouldn't have intersected anyway, right? So it could have happened if this parabola was here all the time, then the two functions don't intersect anyway, then they would have no real root. Okay. Right, so question 6.1, right, it says calculate how many years will it take for the value of a truck to decrease to 50% of its original value, right, if depreciation is calculated at 15% per annum, okay, using the reducing balance method. Okay, now we need to remember, what does this term mean? Okay, reducing balance method. Okay. Right, so in order for us to remember what this is, okay, it's best to contrast it with something else, right? So what is the other method that we use when we look at depreciation? Sorry, right, the other method is straight line depreciation, okay? And straight line is the one that corresponds to simple interest, okay? So if the straight line method is the one that corresponds to simple interest, then it means that reducing balance method is the one that corresponds to compound interest, okay? So we now know that the formula that we need to use, okay, is going to be A, right, which is the depreciated value, right, or what we call the book value. Sorry, I'm still on highlighter mode. Okay, so we're going to have A, right, and this is going to equal to the value that it was originally, right, or we call it the principal amount, into 1, and this time this sign over here is important, right, because we're looking at money decreasing, right, so it's minus, right, interest to the exponent of n. Okay, now this n is what we need to calculate, right, that's the number of years, right. So what is something else they could have added to this to make this a little bit harder? Okay, they could have added a compound period to our interest, right? Notice that our interest is simple, right? It's just 15% per annum, right? So which means that n is going to directly just give us the number of years, right? But they could have also given us interest compounded monthly, right? And then what you would have done is that you would have times this n by 12, right? But now, if you did that, you would have to remember that the question wanted you to give how many years, right? So you would still have to convert the answer you would get, okay? Because you would get in terms of months, right? You still have to convert that into years, right? So that's the little things that you need to watch out for, okay? Right, so now we're ready to just substitute into this formula, okay? Because we are told that the value that we're going to depreciate to, right, so this value of A over here, okay, that is going to be 50% of the original value, right? So we know that the original value is P, right? We're not given amounts over here, so we're going to have to work with the variables, okay? So we can easily now say that this, okay, that this A can be substituted with 0.5 times P, right? So half of P, okay? And then we can just substitute everything else. We're going to have minus 0.15 over here, and it's divided by 1 because it's compounded per annum, right? If you want to, okay, if you wanted to think about it in a more technical term, right? and then you'd have this n, right, times 1 in this case, right? So we can now see that the p's will cancel out because we are multiplying by the p, so we can just divide both sides by p, right, which is going to give us just 0.5 here on the left hand side, and this is now equals to 1 minus 0.15 k to the n, right? I will just simplify what's inside the brackets, even though you don't really need to. Okay, this is equals to 0.85 to the n. Okay, that. So again, we're now just going to use logs to solve for this n. Go straight into exponential form. Therefore, n is equals to log base of 0.85 times 0.5. Okay, so if you plug that into your calculator, you will get that n works out to 4.265, right? And if we round this off, we can round it off to 4 years and a few months. Okay, maybe let's not round it off. Okay, so it gives you n is equal to 4.265024282. And this is years. Okay. Right. We can minus 4 from that, right? And that will give us the decimal, right? Now this decimal is months. Okay, so we can convert this to months, right? So just times it by 12, okay, and you get 3.18, right? So that rounds to 3. So we can say therefore approximately 4 years, okay, and 3 months. Okay, but I'm wondering now if it's actually necessary to give these months, right? Because they only wanted us to calculate the number of years. Okay, so the answer in terms of years is just 4 years, right? It's 4 complete years. Right, I'm not sure, so I would just leave it like that. Right, moving on to question 6.2. Okay, we're now told that every single month, Tepper deposited 1,500 Rand, okay, for his retirement into an account that paid interest at a rate of 9.2% per annum. There we go, compounding period is monthly. Okay, Tepper made his first installment on his 23rd birthday and the last installment 1 month before his 55th birthday. Okay, now we need to calculate how much money is in the account exactly on, okay, his 55th birthday. Right, so this question has a lot of technicalities to it, and the one thing that will really catch you is this on and this before. You need to think about that very carefully, right? So he's making deposits, right? And there's only one deposit amount that we're given over here, so it's an annuity, obviously, and it's for his retirement, so it's going to be a future annuity. Okay, now he's making these payments. He starts when he's 23. Okay, so we're not given here like years and things like that, which is usually what we are given with these questions, right? We're given for how many years do you do this for? Like, so say they say you do this for 5 years or something like that. Okay, so what we are given here is a different point of view. They're telling us that he starts when he's 23 years old, okay, when he turns 23, that specific day. Doesn't matter when that was, whether it was in April or June or I don't care. Basically, when he was 23, he deposited 1,500 Rand towards his retirement, and he started doing that from that point onwards until just a month before he turned 55. Okay, now we need to then determine how much money is in the account exactly when he's 55. Okay, so there's obviously going to be a month, right, where the money is in the account but nothing is happening, but there is something happening. It's gaining interest. Okay, so long as the money is in the account, it's going to gain interest, right? So this money is going to gain interest, 1 month's interest basically. Okay, so we have a future value annuity part here that we need to consider, and then there's this 1 month's interest that we need to consider as well. Okay, so if we just draw a number line, okay, it's going to be quite a long number line. All right, we can recognize that for us, T0, right, is going to be when he's 23. I'll just use his age, okay, to help us, right? That's when he puts in his first 1,500 Rand. Okay, now he's going to do this every single month until he turns the following age. What's the following age after 23? You become 24, right? So now it takes you a year to become 24 years old, right? So this is 12 payments that he makes. Okay, so he's going to turn 24, then he's going to be 54. Okay, and then he's going to be 55, right? But now we stop there. That's the last time we're going to put in a 1,500 Rand. Okay, so when he is 54 years and 11 months, okay, just before he turns 55. Okay, so we need to recognize that in this last period, right, we only make 11 payments. Okay, so that's now going to help us to determine the value of N. Okay, so the value of N is going to be these. How many do we have? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. Okay, so we have 31 full 12 payments, okay, over the year. Okay, and then we also have these last 11 payments that he makes. Okay, so there's one last thing we need to add to this. Don't forget this first payment that he made with A. Okay, so in fact this is incorrect where I put this, right? It should actually be here, right? So when he is 23 and 1 month old, right, from there, right, to when he turns exactly 24, that is a period of 12 months. Okay, so there's this extra payment that he makes over there, right? So we need to add 1 to this. Okay, so plus 1. Okay, let me just help you to think about that. Okay, so let's imagine he turns 23 in April. Okay, so that's April. That's when he turns 23. Okay, the following month, okay, which is May, he's going to be, I'm going to write it as 23.1, okay, years old, right? So 23 and 1 month old, okay. Then it's April, May, June, July, August, September, October, November, December. Then we need to go back to April, right? Because that's when his birthday is, right? So December, January, February, March, and then April again. Okay, basically from here, right, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 payments that you make. Okay, so that's between that first month after his birthday and up until when he turns exactly 24. Okay, so actually I shouldn't write it as point 12. I should actually think of it as now, because it's point 12, he's now turned 24. Okay, right, so if you have a better way to think about this, you can use it, but I usually need to draw everything out and convince myself to make sure that I understand what's going on. Okay. So I'll just move that out the way. That was just to convince you, right? So now when we plug all of this into the calculator, right, this was an important step, because if you get your n value wrong, then everything is just wrong. Okay. So we're going to have 31 times 12, right? Then we're going to have plus 11 and plus 1, or just plus 12. Okay. So that's going to give us 384 payments that he makes, like regular payments. Okay. So now, putting this into the future value formula, right, we've got future value is equals to monthly installment into 1 plus I to the n minus 1 divided by I. Okay. So we now have all the components, and this is now going to tell us how much he's going to have in his account, right, at that point, right? So that point, the month before he turns 55. Okay, so when he's 55 and 11 months, right? Okay, so we have monthly installments of 1,500. This is into 1 plus, what was the interest? 9.2%, which in decimal form is going to be 0.092. We're going to divide that by 12, and this is going to be raised to this n value, 384. Right, and we minus 1 from that, and we still need to divide this by the interest. Okay, so when you plug all of this into the calculator, you get that at that point he has, let's just see over here, 1, 2, 3, oh, he's got lots of money. He's got 3,478,620 rand and 49 cents. Okay, but again, let's go back to the question. Be very careful with these questions. We need to answer the question. We need to calculate the amount of money on his 55th birthday. Okay, so now that 1 month gap that he left over there. Okay, so this 1 month, I know it's squeezed. I hope you can see it. This 1 month gap over there. I don't know why he didn't make a payment then. Maybe he was like, I am tired, or something like that. Okay, so we need to now add some interest to his 3 million rand. Okay, so we are now going to go into, this was FV, but now we're going to go into the compound interest formula, right? So A is equals to P1 plus, this time I to the N, right? That is the P, the 3,478,620.49. And that's going to gain 1 month's interest, right? So it's just 0.092 divided by 12. Okay, and this is just for 1 month. You end up getting that his total amount of money, right, when he's 55 years old is, right, moving on to question 6.3, we have that Abram, right, has 150,000 Rand to invest in 2 separate accounts. Okay. Let's grab a highlighter. One account pays interest at a rate of 8.4% per annum compounded quarterly. Okay. And the other account at a rate of, didn't we have this rate before? Okay, anyway, 9.6% per annum compounded monthly. Okay. How much money should he invest in each account so that he will collect the same amount from each account at the end of 12 years? Okay, so over here, what are we doing? Okay, so we have a set amount of money and we want to figure out how to split this 150,000 Rand into these 2 separate accounts, right? And we want to do so in such a way that at the end of 12 years, okay, we will have the same amount of money. Okay, this is a wow, because this is the first time I ever see simultaneous equations in financial maths. Okay, because if you think about this, at the end of the day, this is just going to be compound interest, right? There's no annuities here, it's just compound interest. Okay, but we know that this variable in our compound interest, okay, so if we just write down the formula, A is equals to P into 1 plus I to the n. Okay, this variable A, right, the amount that we want to accumulate to, it says here in the question that we specifically want it to be the same amount. I don't know why, but okay, that's the conditions that we are given, right? So we are going to have a P1 plus I, okay, for this first account, okay, with its own interest rate, and this is going to be equals to a P, right, 1 plus I for the second account, right, the one with the second interest. Okay, now P is the money we usually start off with, right, and usually it would just be this 150,000 Rand. Okay, but now we want to split it. Okay, so one of these has to be 150,000 Rand minus P. Okay, so I don't know if that makes sense. Let me just write it out on the side. Okay, so if I invest P amount in one account, okay, and I add to that the amount that I invested in another account, which is 150,000 Rand minus P, right? So I invest that amount of money. You can see if we just use algebra for this, if we distribute this positive, you have P plus 150,000 minus P, right? So you can see that the P's cancel out, right? Because you have plus P minus P. So you start off with this amount over here. Okay, gets you back to your starting amount. So I obviously need to invest some P amount in one account, but then in the other account I need to invest 150,000 Rand minus P. Okay, so I'm just gonna erase this and choose this part to be the, to erase that as well. I'm going to choose this part to be, sorry about this, okay, so I'm going to choose this part to be the 150,000 Rand. I'm not going to put the R for now, I'll just put the R's at the end of the day, minus P. Okay, and we still have that bracket 1 plus I to the n. Okay, so if we just move this out the way as well, we can now substitute these things that were given to us, right? So we'll start with the one that is compounded quarterly, right? So we have P into 1 plus, right? So the interest rate is going to be 0.084, right? And it's compounded quarterly, so it's divided by 4, right? And then we have this in terms of years, so we're going to have 12 years, right? Need to multiply this by 4. Okay, that's one way to think about it. Okay, this stays the same. Right, and on this side we have 1 plus 0.096 divided by 12 this time, okay, because it's compounded monthly. And then for every year we have 12 months, right? So we are doing this for 12 years, so we times that by 12. Okay, right. So before I move things around, I don't like how many variables I have so far. So I'm just going to collapse down this bracket, what's inside of the brackets, right? I'm going to collapse this down. Okay. And I'm also going to collapse this down. Okay. So I'm going to have P into, and in your calculator, if you plug in 1 plus 0.084 divided by 4, you get this ugly fraction, right? And this is now going to be raised to 12 times 4, which is going to be 48. This is going to be equals to 150,000. Get my zeros right. Into 1 plus 0.096 divided by 12. We get this fraction. Okay, and then you have 12 times 12, which is 144. Okay, so now we can start a little bit of distributing. Okay, this is still going to stay the same. I'm going to leave it for now. Okay, now we're going to distribute this into the bracket. So we have, let's do it like this, 150,000 Rand times this, okay, minus P times that bracket. Okay, so just basically just distributed this into this bracket. Okay. Alright, so now we can start moving things around. I can now move this, right, because it's like terms with this other factor on the other side. I can move it to the left hand side. That will give me P, right, and I think I'll just take out P as a common factor. So this is now that side. If you take out P as a common factor, you have 126 divided by 125 to the exponent 144. Okay, plus 1021,000 to exponent 48. Okay, and this is now equals to 150,000 times 126 divided by 125 to the exponent 144. Okay. Right, so now I can solve for P, right? So which is the equation, not the equation, the amount that I need to invest in the 1 account, and then if I subtract the same p-value from 150,000 Rand, I'll get the amount that I need to invest in the other account. Okay, so I'm not going to rewrite this, because basically what we're going to do is we're going to divide that side by this whole thing. Okay, so we're going to have just therefore p equals. Okay, so when you plug all of that into the calculator, you get that P is equals to, and I'm going to use the Rand, right? It's equals to 80,000 Rand, 609.5 cents. Okay, so, all right. We need to answer the question here. So I'm going to say, therefore, what's his name? Abram. Yeah, Abram can invest 80,000 Rand, 609 Rand and 5 cents into I wonder now if it matters whether he invested in the one that earns the 8.4 or into the one that earns the 9.6. Okay, so how are we going to determine that? Let's just do it here on the side. Okay, so when I do the second calculation, right, I find that the equal amount, right, happens when you put the 80,000, okay, in the 8.4% account, right, you get this amount, and that's the same as this amount over here, which obviously happens when you put the 69,000 into the 9.6% account. Okay. So I just did these side calculations very quickly in the calculator. You basically just plug them back into this formula, okay, the compound interest formula, and you just do the calculations. Right. So I can go back and say, I've now noted that the 80,000 is going into the 8.4% account. Therefore, Abram, right, will invest this amount, okay, into the account. Sorry, just fix my options here. Okay, into the account that earns 8.4%. Let's do this. Okay, so into the account that earns interest at, I need to move this, 8.4% per annum compounded quarterly. Okay, and the other amount into the account that earns interest at 9.6% per annum compounded monthly. Okay, question number 7 now marks the beginning of differential calculus. Yay! Right. Sorry. So, first question, like usual, is going to be to determine the derivative, right, by first principle. Okay, so we need to remember that this whole first principle thing It's just about applying the definition of a derivative, right? So we need to use our formula. F prime of x is equal to the limit as h tends to 0 of the function f of x plus h, right? This is a new function, minus f of x, all of this divided by h. Okay, and the whole purpose of this whole thing is to substitute h is equals to 0, right? But now the problem is along the way, h is in the denominator, right? So you're going to have to do some simplification until that h disappears, right? As soon as you don't have an h in the denominator, you can then substitute h is equals to 0, and that will give you the equation of a derivative function. Okay, and we need to also remember that that equation of a derivative function is very powerful because it helps us to get the rate of change, right? The instantaneous rate of change of the function. It's giving us the gradient of tangent lines at any point on the function, right? So very, very powerful equation. Okay, right. So let's begin. Right. If we look at this, we see that we already have our first component. Right. So there is f of x given to us very nicely. Okay, so that must just go in here. Right. So we now just need to determine f of x plus h, right? And you can do it in the formula itself, or you can do it as a side calculation. I think in this example, I'll just do it in the formula itself. Okay, so if I plug x plus h in there, right, I'm going to have 2 minus 3 times x plus h all squared. Okay, and then I still have minus, I'll use a bracket, 2 minus 3x squared. This is divided by h. Okay, so moving on from here, one thing that will make you lose marks, right, and they will take marks away from you here because all of this is routine work. You've done these calculations so many times that any slight mistake that you make, it's going to lose you marks. Okay, so one of the most popular places where learners lose marks is that they don't write this notation, limit as h tends to 0, right? They find it tedious, so they decide to stop writing it. You can't, right? You have to write this notation every single time until the point where you substitute, or until the point where you're about to substitute what is this, h is equals to 0, right? So long as you're not ready to substitute h is equals to 0, that notation of limit as h tends to 0, it must be there. Okay, if it's not there, you're going to lose marks. Okay. Right, so to move on from here, what I'm going to do now is I'm going to distribute the contents of this bracket. Okay, so this binomial squared. Okay, and at the same time, I'm going to distribute this negative 3. Right, so you should be able to deal with these double calculations by now. Right, so we have 2 out front. Right, and we know that the first thing we're going to have here is an x squared term. Right, so then we're going to have minus 3x squared. Right, then the next term we're going to have is a 2xh, right? So then I'm going to have minus 6xh, right? And ignore the fact that I like to change the way I write my x, right? It happens. Okay, and then the last term we'll have is an h squared, right? So then I'm going to have minus 3h squared. Okay, so now I'm distributing this negative into the second bracket, so I have minus 2 plus 3x squared. Okay, and this is all divided by h. Okay, at this point what you do is you just check if you have any cancellations, right? And we do. We have a positive 2 and a minus 2. We have a positive 3x squared and a minus 3x squared and a positive 3x squared over there, right? Leaving us with these two terms, right, which luckily for us contain the variable h, which is very good. We now have the limit as h tends to 0, right? We can pull that h out as a common factor, leaving us with minus 6x, right, minus 3h in the bracket, and this is divided by h. Very, very nice, because now we can cancel out this irritating h from the denominator, which was the problem really. Okay, so you can see now you just have that expression. Okay, now because we are ready to substitute h is equals to 0 now, we can now drop this notation. Okay, we just go minus 6x, right, minus 3, and show that substitution. Okay, this is equals to minus 6x. Right, so we can go back and just verify ourselves, because we know the rules of differentiation. We know that the derivative of this 2 would have been 0 anyway, and then the derivative of this minus 3x squared would have been minus 6x, which is good because that always has to be the same answer. If you use rules of differentiation, or you use differentiation by first principle, you must get the same answer, right? It's just that differentiation by first principle is a longer process. Okay, let's go. Next question, 7.2.1, right? This dx, right, is a notation to take the derivative, if you didn't know, right? So what's inside of the dx is our function. Okay, so we are now going to pull that out, and we'll simply start off our solution here as let's say y equal this function 4x plus 5 all squared. Okay, so it's a binomial squared, so we need to distribute it out. That will give us 16x squared, right? And then we're going to have 4 times 5, which is 20. 20 times 2 is going to be 40. So we're going to have 40x, and then we're going to have plus 25. Okay, so now we're going to go on to applying the rules of differentiation. Okay, we're going to do term by term differentiation over here. Okay, and what rule are we applying over here? We're applying the power rule. Okay, so we're going to say that now, therefore, okay, I'm going to now say dy by dx. Okay, this is going to equal, well, for this first term we'll have 16 times 2, which should be 32, right, x, and then we're going to have plus of 40, and that one will die away, right? So that is going to be the derivative. Okay. Next one, 7.2.2, right? We need to determine dy by dx. Again, same different notation this time, but still means derivative. Okay. If y is equals to this blah over here. Okay. Not really such a train smash. We just need to move things around and reshuffle things and all that jazz, right? For this first one, we just need to remember that little concept we talked about in the beginning of this video, right? So moving in between a radical like this and a fractional exponent, right? So we recognize that that value of m, right, can always come underneath and become a denominator to create a fraction as an exponent. Right? So very cool, what do you call it? Third rule to remember. Okay, so we're going to now redefine y. Okay, so we're now going to rewrite y. Okay, we're not changing anything, we're just writing it in a different form that will help us to apply the power rule. Okay, so the first one will change into x to the exponent 1 over 4, right? And then we're going to have plus, right? Now we're going to have x squared minus 8, and we're going to multiply it by this with a negative exponent, so minus 2. Because when we move that x squared to the numerator, the exponent has to change sign. Okay, so after that, we'll have y is equals to x to the exponent 1 over 4 plus, now we're going to distribute this into the brackets. Okay, so when we do that, for the x's are the same base, so we need to add the exponents. So if you add 2 and minus 2, you get 0, so that will give you a 1. Okay, and then you're going to have minus 8 times x to the exponent minus 2. Right, so this is now the function y written in a different form. Okay, so but it's a good form, right, because it's in the form a times x to the exponent of n. Okay, very good form. So now once it's in this form, okay, we can now take the derivative. So we write dy by dx, and that's equals to, it's going to be 1 in the numerator, the 4 will go in the denominator, right, and then we are going to have the new exponent here, we need to minus 1, right? So if we minus 1 is the same as minusing 4 over 4, so we have 1 minus 4 is going to be a minus 3. Okay, so it's going to be in the denominator here. We will change it back to a positive exponent, and the exponent is 3 over 4. Okay, then after that we have plus, well, the 1 is going to go away. Then we have minus 2 times minus 8, which is going to be a positive 16. Okay, and then the new exponent there is going to be minus 2 minus 1, which is minus 3, which will go to the bottom as x cubed. Right, so this is leaving your answer with positive exponents. You could have, I just want to rewrite this, make it more clear, but you could have, if you wanted to, just left it in the step before that I skipped, where you write your answers with the negative exponent. That's also fine. We are not really that picky in our exams in terms of which form you leave the answer in. Okay, so if you're curious about what I'm talking about the step before here that I chose not to show. Okay, so dy by dx. Okay, so before this it was equals to 1 over 4 times x to the minus 3 over 4 plus 16 times x to the minus 2. Right. So you could have left your answer in this form over here. What I did is I moved straight into writing my answer with positive exponents. I don't know, I just like positive exponents. It's up to you what you do. Okay. Question number 8. Right, we now have the graph of f is equals to minus x cubed plus 13x plus 12 is sketched below. A, B, and D, which we have one of the coordinates of D, minus 1, 0, are the x-intercepts of f. Very nice. Okay, so we have 3 x-intercepts for our f function, which is the most that a cubic function can have. It can't have more than 3 x-intercepts. It can have 1, but it can't have more than 3. Okay. And then we have that C is the y-intercept of f. Right, so then it means that it's at the point 12. So there, that should be 12. Right, why do I say that? Because I know for y-intercept I need to set x is equals to 0. So if I plug in 0 there and 0 there, I'll have 0 plus 12, which is 12. Okay, so let's go into the questions. 8.1, write down the coordinates of C. Well, I just told you it's going to be 0, 12. Question 8.2, right, we need to calculate the coordinates of A and B. Right, so now that is calculating these other coordinates, right? So basically we need to factorize that equation over there, right? Okay, and if we need to factorize it, it means we need one factor to start off with, okay? And luckily for us, they gave it to us, right? It's this factor over here, right? And in order for us to write it, this is a x-intercept. But basically, if you put it back into the bracket, it comes from the factor x plus 1, right? So that's our starting factor. Okay, so which means we can rewrite this equation, okay, with this linear factor and our quadratic factor. And now we just need to determine what is that quadratic factor, factorize that further, and that will give us the a and b coordinates. Okay, so remember that to get your quadratic factor, you have 3 methods to choose from, and you can choose the one you want. I think in this video I will use inspection. Yes. Okay, so you can use inspection, you can use synthetic division, or you can use long division, right? And I've covered those methods in other videos on my channel. If you are interested to see them, right, just go to the calculus section and you will find those methods, right? Specifically go to the videos on sketching cubic functions. In one video I use long division, in the other video I use synthetic division. I think in the beginning video I use all 3 of them, so you can see them side by side, the very first video. Okay, but in this video what I'm going to do is I'm going to use inspection because it's the fastest way, right? So what do we have? We have that f of x is given to us as the equation minus x cubed plus 13x plus 12. Okay, now we still need to go through that whole process. These a and b are x-intercepts, so we're going to say for x-intercepts, okay, set f of x equal to 0, right? And I know this is irritating to write down, but write it down. It helps your marker to understand what it is that you're doing. Okay, it guides them through your solution, makes your solution more clear, right? So we then set this equal to 0, that's equal to minus x cubed plus 13x plus 12. Yeah, I'm just going to divide through by negative here. I don't like that negative there. Will give me x cubed minus 13x minus 12. Right, I just want to rephrase what I just said there. It's not about liking the negative, right? It's easier to work with, right? Whatever your leading variable is, it's always easier to work with it when it has a positive coefficient rather than when it has a negative coefficient. Right? So it's not a matter of I like this negative or not. It's actually, the reason is because it's easier to work with a positive leading coefficient. Okay, now I know that this, right, can be factorized into x plus 1, right, times some unknown quadratic factor. Okay, so which means that now all I have to do is just determine this a, b, and c value, right? Right, so now, like said, we are going to factorize this, right, using the method of inspection, right? And there's just one thing we need to remember. Because I decided to divide through by a negative, right, the f of x that we are using now to compare to is going to be this one over here. Okay, the one that we divided through with a negative. Okay, so from here, right, we are now just going to be collecting all the terms, okay, that need to give us the terms that are in this original f of x. Okay, so we need an x cubed term, right? So we can get that by going x times ax squared. Okay, can you see that? Right, so I'll write it here, right? So if we have a times ax squared, then it's going to be ax cubed, right? And that must equal the x cubed term over there, which is just x cubed, right? So then therefore a must equal 1, right? So far we have 0 is equals to x plus 1 times x squared. Okay, we'll skip the b term for now. We'll just go for the c term because it's easy to evaluate. So you can see the only way that you're going to get a constant is to multiply a constant with constant, right? So 1 times c must equal whatever the constant is in our f of x, which is minus 12, right? So 1 times c is c. So we immediately have c is equals to minus 12. Okay, so we have a minus 12 over there. Okay, now next thing is to evaluate this b value, right? But now notice that you can get an x squared term, right, in two different ways. Okay, you can have x times bx, right, and you can also have 1 times ax squared, right? Both of those will give you an x squared term. Right? Now if we compare it to the original function, we see we don't have any x squared term, but that doesn't mean that we don't need to write it down. The equation is going to look like this, right? So it's x times bx, which is going to be bx squared, right? And we're going to add to that 1 times ax squared, but a was also 1. So this is just 1 times x squared, which is just plus x squared, right? And this must equal the number of x squared terms we originally had, and we had 0 of them. So we had 0 x squared terms, right? So if we combine this, right, we have, let's take out x squared as a common factor, which will leave us b plus 1 in the bracket, and that's equals to 0 basically, right? Anything divided by 0 is 0, so this is b plus 1 is equals to 0. Okay, so then therefore b must equal minus 1. Right? So this is minus x there. Okay, so this is the whole inspection thing, but you would generally do that in your head or in your calculator. Right? That's the whole point of saying that you're doing this by inspection. Right, so if you use those other methods, right, so synthetic division or long division, right, you should get this as your quadratic vector, right? So x squared minus x minus 12, right? Now we just need to factorize this, right? So let's see. We have x plus 1, okay, and 4 times 3 is 12, right? So we are going to need a minus 1 in between, so we need minus 4 and plus 3. Okay, so then therefore setting all of these factors equal to 0, okay, that will give us our x-intercepts, right? So we already know about this one. X is equals to minus 1, x is equals to 4, and x is equals to minus 3, right? So we're going to have to go back to the sketch to determine who is who. Okay, so there's the minus 1, right? This is going to have to be the minus 3, and this is going to have to be the 4. Okay, so we now need to conclude that, because remember we asked to calculate the coordinates of A and B. So we have to now conclude, right, that A is the minus 3, 0, and B is the 4, 0. Okay. So moving on to question 8.3, we now need to determine the point of inflection of g, right, if it is given that g of x is equals to minus f of x. Okay. Something interesting about this, if we go back here, right, to the previous question that we just did, remember we went through a step, right, where we multiplied f of x, right, through by a negative, okay, and we obtained this equation over here. Okay, that is basically the equation of g of x, right? So if you multiply it by a negative, you're basically just flipping this graph, right, about the y-axis, right? So this just flips over. Okay, so g of x is going to look like this, right? All right, mine doesn't look so pretty, right? But basically, this would be g of x, okay? So if you just multiply f of x, right, by a negative, you're just reflecting it over the x-axis, right? So g of x will look like this. And luckily for us, we already sort of indirectly determined the equation of g of x, right? It's this equation right over here, right? So it's x cubed minus 13x minus 12. Okay, so we're going to use this equation in this question, okay, to determine the point of inflection, right? And we know that we are going to have a point of inflection when the second derivative is equals to 0, right? And we don't really necessarily have to test that. For us, it's always the case, okay? So we just saw that g of x is going to be equals to x cubed minus 13x minus 12. Okay, so when we differentiate this for the first time, okay, we get 3x squared minus 13x, no, minus 13, sorry, right? And then when we differentiate it the second time, okay, we'll just have 6x. Okay, so then when we set g double prime of x, right, equal to 0, this is to find the point of inflection, right? I'm going to abbreviate it. So point of inflection, POI. Okay, so then therefore 0 is equals to 6x, right? Dividing both sides by 6, sorry, you get x is equals to 0, right? We're looking for the point, right? We already know that when x is equals to 0, right? If you plug it into that equation there, then your point of inflection is basically at the same point as the y-intercept, okay? So the point of inflection is going to be given by the point 0, 12, minus 12, sorry. Okay, when you substitute 0 in there and in there, okay, back into the original equation. Right. So that takes care of that question. Question 8.4 then says calculate the value or the values of x for which the tangent to f is parallel to the line y is equals to minus 14x plus c. Right. Now with these questions, basically what they're giving you here, or what is going to be the most important to focus on, is this gradient. Okay. So if you are going to have tangents that are going to be parallel to the specific line, right, your tangents must have the same gradient as this, right? But then now we know that for tangents, right, their gradients are defined by the derivative, right, of the function of f, right? So we'll just rewrite f of x, right? So f of x was the minus x cubed, right, plus 13x plus 12, right? This was f of x. So when we differentiate f of x, we get minus 3x plus 13, okay? So we now need to set f prime of x, right, equal to minus 14, okay, if we want our tangents to be parallel to this line. Okay, so basically what we're doing is we're looking for now the x values where the tangents to f is going to have a gradient of minus 14. Okay, so if we do that, we'll have minus 14 over here, and that's going to equal minus 3x plus 13, right? I think I'll move the 3x to this side and then have 13 plus 14 on the other side, giving me 27, right? So then therefore, right, did I differentiate this wrong? Yes. this has a square over here. Sorry about that. Yeah, I must be a little bit careful now because I'm getting a little bit tired, so I am making a little bit clumsy mistakes. But basically, if we just go back here, I just realized that this was x cubed, right? So I missed a 2 over there, right? So minus 3x squared, and I just rectified it now, right? So dividing both sides by 3, you see now I'm writing 3. Ah, gosh. Okay, so x squared, right? This is going to equal 9, right? So then from here, you can already see this is going to be a difference of squares, or you can just take the square root of both sides, considering the plus or minus, right? So then I can immediately say that therefore I'm going to have a tangent at x is equals to 3 or at x is equals to minus 3, right? So at any of those two x values, if you draw a tangent to f, it's going to be parallel to this line y is equals to minus 14x plus c, right? What was the question? The question was to calculate the value or the values of x, right? So that's where we leave it. It's at the x value of 3, and the other one is going to be an x value of minus 3. Okay, so I think if we just go up and we visualize it, okay, and now you can see that these lines would be parallel to each other. Okay. Right, and the line minus 14x plus c, right, would be any line parallel to these two, cutting the y-axis and on the positive side, basically, right? So something like this would do. Okay, so this could have been the line y is equals to minus 14x plus c, right? Whatever that c value would be. Okay, so long as it's on the positive side, because they said plus c. But that's not important. The important thing is that the gradients, right, are equal to right. The gradient of this is minus 14, and the gradient of this is minus 14. Okay, they're obviously going to have their own equations as well. Okay. Question number 9, right, we have a right circular cone with a radius of P and a height T cut out. Okay. So we are cutting it out from a solid sphere, okay, with a center C. That's important to know. Okay, so if this is the center there, okay, that's C, it means that this all the way up to the circumference of the sphere, that's capital letter R. Okay, that's the radius of the sphere. Okay, so I'm going to have capital letter R as the radius of sphere. Okay, and that equals to, I think they'll tell us, yes, 30 centimeters. Okay, and this is as shown on the sketch, right? They also give us the equation of the volume of the sphere over here and the volume of a cone right over here. Another key thing that we need to take from this is that they told us that we're working with a right circular cone, and that word right is speaking to this angle right over there. You can see it there. It's the right angle there that they're talking about. So this right angle triangle, right, ABC, is going to be very important to us. Okay. A is basically the center of this cone, right? So this distance AB is small letter r, right? But we already have a variable there, so basically this variable p, right, is denoting the radius of, I'm just going to say the cone. Okay, so now you need to because this is going to become an optimization problem, obviously, you need to realize what it is that is going to change over here in order for us to have a question, right? So obviously what's going to change, right, or be variant is this height t, okay? Because you can imagine if you pick the points, right, of the base of the cone to be a little bit higher up, okay, then you'll have this fat right angle cone like that, and the value of t, right, which is the distance from this top point to the center of this cone, that will be different, okay? And also if maybe let's say you pick it to be very low down, right, giving you the skinny like cone, right, then the value of t is also going to be different, right? So now because this value of t is changing, they're definitely going to ask us to find out which value of t, right, is going to be the best one. Maybe I'm pretty sure they're going to talk about to maximize something, right, to maybe to get the maximum volume of this cone, right? So let's just go to the questions and see what they say. Okay, so 9.1.1, we have from the given information express the following. AC in terms of T, right? So let's just go back to the sketch, right? So AC is this distance over there, okay? So I am just going to, well, it's very easy to represent this in terms of T. If the whole distance is T, if you just minus the distance of the radius of the sphere, then this, right, AC, that becomes T minus 30. Okay. Right, so we can just say over here, AC is equals to T minus 30, and it's going to be in units of centimeters. Okay. Next, we are still using the information given. We now need to express the following. P squared in its simplest form in terms of T. Right, so P squared is going to come from this right angle triangle. Right, let's just redraw it. Okay, so we have this situation going on. Right, we've got the center of the sphere over there. We've got this base point A over there. We just determined that this is T minus 30 centimeters. Right, we were given that this is P centimeters. Okay, and we know that if that's the center, that goes all the way up to the circumference of the sphere. So that's the radius of the sphere, which is 30 units or 30 centimeters long. Okay, so there's 30 over there. Now we need to express P squared. So we're just going to write an equation for P squared, and that's going to come from Pythagoras theorem. That's going to be the square on the hypotenuse, so 30 squared minus the square on the other side, so T minus 30 squared. Right. We need to express it in its simplest form, which means that we need to simplify this. Right, so we're going to have P squared is going to equal 30 squared minus, right, let's distribute this out. We still have a bracket. This is going to be T squared minus 60T and then plus 30 squared. Okay, so we're going to have P squared is equals to 30 squared minus, why did I write a degree sign there? Okay, 30 squared minus T squared plus 60T minus 30 squared. Okay, so the 30 squared obviously now just cancel out, leaving us with P squared is equals to, I'll write it with the 60T first, right, just to have a positive coefficient in the front, minus T squared. Okay, so that is going to be an expression for P squared in its simplest form, and it's also in terms of T, right, so 60T minus T squared. Okay. Question 9.2, we need to show that the volume of the cone, right, can be written in this form. V of t, right, is equals to all of this, right. So we're going to have to grab hold of these equations, right. So we have V is equals to 1/3 pi, right, r squared, and our r in this case is going to be p. And that's going to be nice because we just determined an equation for p squared. Let's just go grab it. And we were given that the volume of the cone, right, let me just leave that c out, right, that is 1/3 pi, right, r squared, which in this case is going to be p squared, right, times the height. Okay, yeah, there we go. Right, now the height of the cone, right, we were told even over there it's a height of t, but you can also see it on the diagram, right, perpendicular height. Okay, so when we substitute this, we'll have 1/3, okay, pi, and we'll substitute p squared, which is 6tt minus t squared, and then we still need to multiply this by the height t. Okay, so everything here is being multiplied by each other, right? So we are just going to have, right, we'll distribute these two things, right, at the same time. Okay, so the first thing we're going to have is 1/3 times 60, okay, and that will give us 20, right? So this is what we're doing now. Okay, we're distributing that. Okay, so 1/3 times 60, that's 20, and then we still have the pi, and we still have the t, but the t times that t will give you t squared. Okay. Next, now we are distributing this to the second term. At the same time, we'll distribute the t as well. Okay, so we are going to have, first of all, we'll have minus 1/3 pi, right, and then the t squared times the t will give a t cubed, right, like that. So if we just check over here, okay, we have the 20 pi t squared minus 1/3 pi t cubed. Okay, so we've shown exactly what they wanted us to show. So then this is therefore v of t, because it's the volume of the cone in terms of the variable t. Okay, let's copy this because I'm sure we have to optimize it now. Okay, question 9.3, right, now wants us to calculate the value of t for which the volume of the cone will be a maximum. Okay, that's very good. We'll just grab our equation for v of t. Right, there it is. And what we want to do now is to differentiate this, okay, and then set that derivative equals to 0 to get our critical points, right? And then we'll just test our critical points to determine where are we going to have maximum and where we're going to have a minimum. Okay, so if we differentiate this, we'll have v prime of t, okay, and that's going to equal 20 times 2, which is going to be 40, right, pi, times t, okay, and then we're going to have minus the 3 times the 1/3 will be a 1, and we'll still have the pi times t squared. Okay, so then we're now going to set v prime of t equal to 0, right, and we're doing this to find our critical values. Sorry. Okay, so this is for critical values, right? We're setting v prime of t, basically setting the derivative equals to 0, right? And then we're going to have 40. Let's actually do this. It is a common factor of pi here. Let's pull it out, and we'll be left with 40t minus t squared. Okay, so then we can divide both sides by pi, right, which will give us 0 is equals to 40t minus t squared. Okay, again we have a common factor of t, so we can pull that out, leaving us with 40 minus t. Okay, so these are our two factors. Okay, and that's going to then have that therefore, okay, but this is not just critical values, t must equal 0 or t must equal 40. Okay, and this is t was the height of the cone, right? So it's in units of centimeters, and actually we won't even need a first derivative test over here because the one answer makes absolutely no sense. If t is 0 centimeters, then what you have is not a cone anymore, but rather nothing. You have a disk, basically. So if we just draw that setup again, there's the sphere. T was the height, okay, from the base of the cone, right, from the base of the cone to the top part of the sphere. So now if t is 0, you don't have that top part. So what you have inside the sphere is just a disk. Okay, so some flat horizontal piece of paper, if you want to think of it like that. So if we want the volume to be maximum, right, this is 0 volume if you're considering a cone, right, because this is no cone basically. So this is not applicable. Okay, so it's definitely just going to be when t, what we were asked to find, we were asked to find the value of t. Okay, so we were not asked to find what is the maximum volume, so we just need to report what is the value of t that will give that maximum volume. That is going to be when t is equals to 40 centimeters, right? But let's just, for argument's sake, do a first derivative test just to confirm for us, right, what that would look like on the number line, because sometimes the answer doesn't pop out like that. So with the first derivative test, right, you draw your number line and you would put v prime over here to help you to remember that what you are now substituting into, okay, is the v prime formula. Okay, so there it is. Okay, I've cut it off a little bit there, but you get the point. Right. So you would put these critical numbers on the number line like usual. Right. So you'd have 0 and you would have 40. Right. So what you would then do is you would take your calculator and you type in the equation. So it's 40 pi times t minus pi times t squared. Okay. So when you substitute in a negative number, right, so a number less than 0, right, let's say t was minus 2, but then actually if you think of the domain, right, of this, right, this is actually a domain of t greater than 0, right, so because you want a volume loss, it's useless to have t equal to 0 in the original equation anyway, right? So in fact it makes no sense to check a derivative before this. Okay? I just fix my logic over here, right? So it makes no sense to check a derivative before a t value of 0. Okay, so we'd actually start here at a t value of 0. Okay. So we check in between. Alright, so let's say something like 11 centimeters, right? And you would get a positive result. Okay, so you get a positive result, right? So it means that on the graph of this function, okay, this function v of t, okay, from 0 to 40, right, you have positive gradients, right? So the gradients on the function are increasing, okay? Then you would pick a number greater than 40 centimeters. So let's say 56. and you get a negative result, right? So you get a negative over here, right? Which tells you that the gradient of the tangent lines on the graph of v of t, right, for this interval, they now start decreasing, okay? So what the function is doing, okay, is that it's increasing for t values less than 40 but greater than 0, right? And then it's decreasing for t values greater than 40, right? And because we have this increasing then decreasing situation happening, then this confirms for us that here at a t value of 40, you have a local maximum. Okay, so then we can be assured that this t value of 40 centimeters is actually the one that will give us exactly what they asked, right? The maximum volume of this cone. Okay, and if you want to know what that maximum volume is, you are going to have to substitute it into the original formula. Okay, substitute t is equals to 40 into the original formula, and that will give you the volume of the maximum volume of the cone. Right. Question 9.4. Right. We now asked what percentage of the sphere was used to obtain this cone having maximum volume. Oh, okay. So now we actually have to determine that maximum volume. I think I still have the equation. Yeah, there we go. Right. Oops. All right. So there's the volume of the equation, right? Basically, that describes the volume of the cone for different values of t, right, with a domain of t greater than 0, right? Okay, so now we want to find out what percentage of the sphere, okay, was used, right? Well, we need to know what is the volume of the cone first of all, right? And we're looking at the maximum volume, so that was V of 40. Okay, that will equal 20 pi times 40 squared minus 1/3 pi times 40 cubed. Okay, and that will give us something in units of centimeters cubed, right? Because it's a volume. Okay, so when you work this out, it works out to 33,510.32 centimeters cubed, right? So that's the volume of the cone, right? The maximum volume of the cone, right? So I'm gonna keep that answer in the calculator. Okay, and now we need to find out what was the volume of the sphere. Okay, so going back up, we have 4/3 pi r cubed, right? So we're just going to have 4/3 pi, and our value for our sphere was specifically 30 centimeters, and that's cubed, right? So that's the volume of the sphere. Okay. Okay, so if you work this out in your calculator, you get the total volume of the sphere was 113,000, okay, and 97.34. It's also going to be in centimeters cubed. Okay, so now if we want the percentage of the sphere occupied by the cone, okay, that is going to be the volume of the cone, right? So I'll just write it like this: volume of the cone divided by the total volume, which is the volume of the sphere, times 100. Okay, so if we substitute those values, we get, okay, so we'll just use, make sure you use the full decimal numbers on your calculator. Okay, and this works out to a percentage of 29.6. It says 6296, so I'll round it up to 2 decimal places, 63%. Okay, so what percentage of the sphere is occupied by the cone when the cone is at maximum volume? Well, only 29.63%, right, of the cone is occupied by volume, basically, okay, because we calculated this percentage. Okay, so it's in terms of volume. Okay. All right. Question number 10, right? We're almost done with this paper. Hope you guys are still with me, right? We now have that Ben, Mtantla, Owen, Derek, and 6 other athletes, right? So this is 1, 2, 3, 4 people that they mentioned, plus there's 6 is going to make 10 different people that we have, okay? And they are taking place in a 100-meter race. Each athlete will be allocated a lane in which to run, okay? The athlete's track has 10 lanes, right? So obviously now we are in the realm of fundamental counting principle and permutations and all of that, right? Just for the people that understand what's happening here, okay? If you wanted to use the permutation formula for this, right, to figure out, I'm basically already looking at this first question, right? So 10.1, in how many different ways can all the athletes be allocated to the lane, right? So if you look at what's happening here, we have 10 lanes and we have 10 athletes, right? So using the permutation formula, if you wanted to, right, it's an equation that, or a formula that not everyone understands, but if you do understand it, right, I'm now accommodating you, right? This is a situation where you have 10, pick 10, right? And whenever you have the same numbers on the two sides like this is equals to 10 factorial, right? So basically we are saying here, right, when we say 10 pick 10, or if you use the technical terms, 10 permute 10, right? So how many ways can you permute 10 people, okay, from 10 people? Well, it's 10 factorial ways, right? So if I can put it in a different way, right, you can think of this as being a situation where we want to arrange 10 distinct items when we are given 10 distinct items. Well, we always arrange distinct items in 10 factorial ways. Okay, so let me just show you why when the n and the r, right, are the same values, why do you end up with just the 10 factorial, right, or these two numbers factorial? Okay, so remember that in general it says n PR. Okay, so you have a total of n items, n distinct items, and you just want to arrange a select few, right, that are. The general formula says n factorial divided by n minus 1 factorial. Okay, that's our permutation formula. Okay, now if you are looking at 10 pick 10, right, that's n, that's r, so you have 10 factorial divided by 10 minus 10, basically all of this factorial. Okay, so we still have to first evaluate what's inside the bracket. So 10 minus 10 is 0, okay, and 0 factorial, funny enough, is defined as 1. Okay, so this is actually just 10 factorial. Okay, so remember, we don't leave a factorial like this. We have to evaluate it. So if you punch in your calculator 10 factorial, then you get that these athletes, okay, can be allocated on these 10 lanes in, just count here quickly, 3,628,800 different ways. So if you are not the type of person who is going to go to the permutation formula to solve this, it's fine, because we still teach you the basics that just say that if you want to arrange n distinct items, right, that can always be done in n factorial ways, right? So you would have come to the same answer anyway, because these are 10 different people, right, and you want to arrange them, okay, and you can do that in a total of 10 factorial ways, right? Okay, so 10.4, we now have one of those restrictions. They say 4 athletes taking part in the event insist in being placed on lanes next to each other. Alright, so we've got fussy athletes over here. There's 4 of them that want to be next to each other. Maybe we can just assume it's these 4 over here, Ben, Glantler, Owen, and Derek, right? They are the culprits that want to run next to each other, okay? In how many different ways can the lanes be allocated now, right? So I'm just going to go back to the previous question and grab onto this answer, because this is the total number of ways that we can allocate these athletes without any specific requirements, right? Without any fussiness, okay? So we'll put it down over here. So now we're going to determine how many lane allocations can we make now with this restriction, okay? And I think I'll just use the method that most teachers will teach you, okay? Which is to say that if you are now going to group these 4 people together, they end up forming their own group, right? So that group has 4 people in it. Yeah, I'm just going to quickly sketch them. There is it 1, 2, 3, 4. Okay, so we bundle them up, right? And then we still have those 6 other athletes. Okay, so 1, 2, 3, 4, 5, 6. Okay, so if we look at the number of arrangements, right, that we can make with 4 athletes running next to each other, okay, that is going to equal, well, first of all, we now have 1, 2, 3, 4, 5, 6, 7 distinct items, okay? So we're going to have 7 factorial, right? But then we still need to multiply that by the arrangement of these 4 athletes inside of this little box, and they can rearrange themselves, okay, in 4 factorial ways. Sorry. So if you think of the situation, right, so I'm going to try and represent it. Okay, so there is our starting line, okay, for their 100-meter race, and there's these 10 lanes, right, where they can be placed, right, or allocated. Okay, so what we're saying now, okay, is that 4 of them want to be put in a specific place, but they want to be next to each other, right? So they want to specifically want to, maybe let's say, take these first 4, right? 1, 2, 3, 4 lanes, okay? They want to be next to each other there, right? But the thing is, they just want to be next to each other. It doesn't necessarily have to be these first 4. It can be the next 4 or anywhere along here, so long as they're next to each other, right? So that movement, okay, together with the movement of these other 6 people, that's represented by that 7 factorial, okay? And then now another thing that they're not really being picky about, okay, is that if you concentrate on these specific 4 lanes, let's say they are on these first 4, they're not being picky about, is Derek going to run here, or is Derek going to run there, or is Ben going to run here, or Ben going to run there, right? And maybe Klantla must run here, or is he going to run here, or is he going to run here? It doesn't really matter, okay? They can shuffle around, Okay, and that shuffling around is represented by this 4 factorial. Okay, so from there we have 7 factorial times 4 factorial. Okay, and we get 120,096 ways, okay, that have this specific restriction. Okay, what were we asked to answer here? We were just asked to answer, I lost the question now. Okay, in how many different ways can the lanes be allocated now? Okay, this is the answer for this question. So we don't actually need that. Okay, sorry, I thought that they asked us how many ways can the lanes be allocated if they are not next to each other. So if it was not next to each other, then you take this total and subtract this over here where they are next to each other. Okay, so this is the answer. Okay, just this is the answer to question 10.2. Okay. Okay, question 10.3, right, it says now, if the lanes are randomly allocated to the athletes, right, so that is the situation we were looking at in the beginning, right, where you have no restrictions whatsoever, you just allocate them whichever way, okay. Determine the probability that Ben will be placed on or in the first lane, Klantler in the third lane, Owen in the fifth lane, and Derek in the seventh lane. Okay, so we're still going to need this. Okay, this total number of lane allocations without restrictions, right? Because that is talking to this part. Okay, this random allocation. Right. So now we have to determine in how many ways can we arrange or do the lane allocations with these specifications, right? So we can take it as restrictions. So I'm just going to say number of arrangements. Okay. And if I just sketch it out, we have 10 positions. So 1, 2, 3, 4, 5. 6, 7, 8, 9, 10. Okay, this is also representing the lanes, right? So what they're saying is that Ben wants to be on the first lane. Okay, so he wants to fix himself over there. That's Ben. And then Klantler wants to be on the third lane, so he wants to be there. So that's in Klantler. Owen wants to be on the fifth lane, so he wants to be over here. And Derek wants to be on the seventh lane, right? So he wants to be over here. Okay. So now if we fix these 4 people, right, we just have these 6 people to play around with. They can shuffle around. Okay? They don't care, right? They can move around in between them. Okay. So they can arrange themselves in 6 factorial ways. Okay. So then the probability, right, so probability, right, so we know that it's always going to be the number of elements that are desired divided by the sample space. Okay, and we know now that the desired arrangements, okay, will be given by 6 factorial, and the sample space is given by that, right, and that is 3,628,800. Okay, so evaluating this in the calculator, you get 0.000198. Okay, it's a very low probability. Okay, if you times this by 100, it becomes 0.01. I'll write it as 98%. Okay, so it's less than 1%. Oh, so very much highly unlikely to happen. Okay, that if we do a random allocation, that Ben will be over here on lane number 1, Tlantla will be here on lane number 3, Owen will be on lane number 5, and Derek will be on lane number 7. Okay, very unlikely. Question 11, right? We now have a survey on their preference of exercise was conducted amongst a total of 140 people in 2 age groups, right? And what we have over here is a contingency table. The information is summarized below, right? So we have tennis, running, and gym, okay? And we have the age groups 35 years and younger, okay? So this is an age of anything less than or equal to 35, right? And older than 35 years, right? So just greater than 35 years, okay? So we have these variables A, B, C, and D, which are unknown. 11.1 says, if it is given that preferring to play tennis and age are independent to each other. Okay, so playing tennis and age, right, are independent of each other, determine the value of A. Okay, so you need to play tennis, right? So in that column, and then we need to have an age. Okay, since we need to determine the value of A, it means that this age group, right, because that's where A intersects, right? So being younger than 35 or equals to or 35 years old, right, is independent of your preference for playing tennis, right? So we know now that these two events are independent, and while independent events have the identity probability of A times the probability of B, okay, is equals to, okay, so where we're going to define A to be the event of playing tennis and B to be the event of being 35 years of age or younger and younger, okay, this will equal the probability that you play tennis and you are 35 years of age and younger, okay. I don't even know why they said in here. I think it's better to say or younger, but then, okay. Right, so let's look at this. What is the probability that you will play tennis? Okay, from this group, well, there was a total of 21 people that preferred tennis. Okay, from the 140 people surveyed. Okay, this is going to be times, what is the probability that you are 30 years and younger? Well, there were 80 people surveyed in that age group out of the total 140. Okay, this must equal the probability that you play tennis and you are in this age group. Well, it's only those people that meet that requirement. That's A, number of people over the total. Okay, so now we can determine this value of A that they're looking for. Okay, so what can we do over here? We can have 21 times 80, okay, giving us 1680 in our numerator, and in the denominator I'll just write it as 140 squared. Okay, this will equal A divided by 140. Okay, so I'm going to cross multiply. I'm going to have A times 140 squared is equals to 1680 times 140. That will give me 235,200. Okay, A equals 12 people, right, that prefer to play tennis and are in the age group 35 years and younger. Okay. Okay, question 11.2, right? They now say if it is given that a is equals to 12, that's nice. Now we know that we've calculated our a value correctly, right? This was just to help you if you didn't get the right answer above, or if you couldn't figure out the question, then at least you could still, answer 11.2, right, by taking this as true. We now need to determine the probability that a randomly selected person prefers going, let me just use a highlighter, right, so prefers going to the gym, okay, or is in the age group 35 years and younger. Okay, so this one is just an application of the addition formula. Okay, so remember that, okay, now we're just going to have to redefine our variables here. So we'll define A as the event of preferring going to the gym, okay, as your method of exercise. And we'll define B to be the event that you are in the age group 35 years and younger. Okay, so if we write down the addition rule, okay, if we're looking for this probability, what is the probability that you prefer going to the gym or you are in this age group? Okay, probability of A or B. That's going to equal the probability of A plus the probability of B minus the probability of A and B. Okay, so the probability that you prefer going to the gym and you are in this age group, right? So that we can get from a contingency table like before, okay? So if you're in this age group and you prefer going to the gym, then you are these number of people here, right? So C number of people, okay? And that's why you needed this value of A, okay? Because A plus 28 plus C is equals to this total of 80, okay? So if A is 12, you have 12 plus 28 plus C is equals to 80, right? So then therefore you get that 80 minus 12 minus 28 gives you 40 people, right, that answered in this survey in this age group that they prefer going to the gym as their form of exercise. Okay, so we know that 40 is going to belong over here, right, in this AND, but this is a probability, so it's divided by the total number of people. Okay, now what is the probability that you just prefer going to the gym, right? Just prefer going to the gym. Well, there was a total of 70 people that indicated that they prefer going to the gym as their form of exercise. Okay, so we have over here 70 divided by 140. Okay, plus what is the probability that you are in this age group? We already determined this, right? There's a total of 80 people who were surveyed in that age group. So we have 80 divided by 140. So now it's up to the calculator. Okay, and we get a probability of 11 over 14, which equals 0.79, if we round it off to 2 decimal places. Okay, so we can rewrite that as 79%, right? So there is a 79% chance, right, that if you pick someone at random from these specific group of people, right, these 140 groups of people, right, there's a 75% chance that the person you're going to choose is going to prefer going to the gym or is in the age group 35 years and younger. Okay, and that brings us to the end of this question paper, right? I hope that helped matriculants. This was the May-June paper for 2018, right? And As always, remember that at the end of your question paper, you are going to be given an information sheet. So if you want to call it a formula sheet, if you want to, you can reference this if, for example, you forget signs like with the future and the present value formula. If you forget, must it be a plus, or must it be a minus, or so on and so on. But obviously, don't rely on this formula sheet. Always try to have all of these formulas memorized or committed to memory, right? It helps you to move a little bit more faster. Okay, so with that said, I will see you guys next time.